You sit in the command seat of a spacecraft designed specifically for deep planetary exploration. Your vessel is equipped with reinforced shielding to withstand extreme pressures and temperatures. And ahead, through the forward window, Saturn appears as nothing more than a bright point of yellowish light against the darkness of space. The journey from Earth's orbit to this location in the outer solar system has taken years, your spacecraft following a trajectory that carried it past the inner planets through the asteroid belt, beyond Jupiter's orbit, and now finally approaching the realm of the ringed giant. Saturn orbits nearly 10 times farther from the Sun than Earth does, placing you so far from the solar system's center that sunlight arrives weakened to roughly 1% of its intensity at home. The Sun itself appearing smaller and less commanding than you remember from the inner system. The control panel confirms your approach parameters, velocity and trajectory bringing you gradually closer to that distant point of light over the coming days and weeks. The spacecraft holds a steady velocity relative to Saturn, and over the hours that follow the point of light ahead, grows perceptibly larger as the separation decreases. What began as a star-like point swells into a small disk, the change happening slowly enough that you must compare mental notes from earlier observations to confirm the growth. The color strengthens as the disk expands, a pale golden hue distinguishing Saturn from the white and blue points of stars scattered across the background. You find yourself checking the view more frequently as the days pass, watching for changes that mark your progress toward the giant planet. You are listening to the Drowsy Astronaut, and tonight we are taking a slow journey toward and then into Saturn. Beginning here in the outer solar system as we approach this giant planet and continuing inward through its rings and deep into its atmosphere and interior. This journey will unfold gradually across the coming hours, following the spacecraft's descent from approach through ring passage and atmospheric entry all the way to Saturn's core. Exploring each environment thoroughly as we encounter it. If you are comfortable, you might share in the comments where you are listening from tonight. And if you find value in these long-form explorations, you might like the video or subscribe to join us on future voyages through the cosmos. The journey continues as Saturn grows larger ahead, and the planet begins to reveal features that were invisible only days ago. Days pass as the spacecraft continues inward, the automated systems maintaining the approach trajectory, while you spend hours at the observation windows watching the slowly changing view. Saturn has transformed from a small disk into something clearly planetary, a world rather than just a bright object. The rings appear first as a thin, bright line extending to either side of the planet's equator, their presence confirming that your approach angle gives you a view of the ring system, tilted rather than edge-on. The planet's outline looks slightly flattened at top and bottom, even before you can make out other details, the shape hinting at rapid rotation that deforms Saturn's fluid body. The golden color deepens as more light reaches you from the growing planetary disk, and you start noticing subtle variations in brightness across Saturn's face. The overall appearance strikes you as gentler than Jupiter's dramatic coloring, which you observed during the earlier portion of your journey through the outer solar system. Saturn's cloud tops present pale yellows and creams rather than vivid oranges and browns. The rings continue brightening as their angular separation from the planet increases, the structure beginning to look dimensional rather than like a simple line. You can see both their top surface and their extension outward from Saturn's equator now. Horizontal banding appears across Saturn's disk as you close to within several million kilometers, faint lines parallel to the equator, marking boundaries between atmospheric zones. The bands look subtle compared to Jupiter's pronounced belts and zones, requiring careful observation to distinguish them clearly. Light zones alternate with slightly darker belts, the pattern circling the planet at different latitudes. Rising gas in the zones brings bright clouds to high altitudes, while descending gas in the belts allows deeper views into darker layers. You spend time at the window just watching these patterns, the bands more apparent some days than others, depending on lighting conditions and the atmospheric state. The control panel shows readings from the magnetometer as the spacecraft enters the outer reaches of Saturn's magnetic influence. Charged particles from the solar wind encountering the planet's magnetic field and creating a boundary region. The magnetosphere extends millions of kilometers into space, far beyond the ring system. Radiation levels tick upward on the monitoring displays as you penetrate deeper. Energetic particles trapped in Saturn's radiation belts, creating an environment that the spacecraft shielding handles without difficulty. You note the readings, but return your attention to the visual observation, the instruments confirming what matters while the windows show what captivates. Saturn now fills a substantial portion of your forward view, its size no longer requiring mental comparison to earlier observations to appreciate. The planet looks enormous, its equatorial diameter measuring 9 times Earth's width, large enough to contain more than 700 Earth-sized worlds within its volume. The flattened shape appears obvious now, the equatorial bulge and polar flattening, creating a clearly non-spherical outline. The 10-hour rotation period generates forces strong enough to deform the planet's fluid body visibly, the effect more pronounced on Saturn than on any other planet you know. You can almost sense the rapid spin just from looking at the shape. Details fill in across the atmospheric banding as distance decreases, and you begin distinguishing individual features within the zones and belts that circle Saturn's globe. Small oval structures appear at various latitudes, storm systems embedded in the larger flow patterns. Bright or dark spots mark convective activity rising from deeper atmospheric levels. The boundaries between zones and belts show complex structure where different atmospheric bands move at different velocities, these boundaries hosting the fastest winds in Saturn's atmosphere. You watch one particular bright oval for several hours, tracking its motion against the background banding, the storm drifting steadily with the wind pattern that carries it. The North Polar region reveals something extraordinary, as your approach angle allows better viewing of Saturn's northern hemisphere, and what you see there takes a moment to comprehend. The atmospheric flow organizes into a hexagonal shape centered on the pole, 6 straight sides meeting at sharp corners in a configuration that seems impossible for fluid gas. Each side of the hexagon stretches longer than Earth's diameter, the entire pattern encompassing an area large enough to contain several Earth-sized planets. The formation represents a wave in the jet stream that circles the North Pole, somehow locked into this geometric configuration. The center of the hexagon contains a darker region, marking a cyclonic vortex sitting at the pole itself. surrounded by the geometric flow pattern. The south polar region shows different characteristics. Visible as Saturn's sphere, allows you to observe both poles from your current distance. The southern pole hosts a central vortex without the hexagonal pattern present in the north. The southern storm appearing as a dark oval surrounded by lighter cloud material, spiraling inward. The structure rotates around the pole. As Saturn spins beneath it, the entire system organized differently than the northern hemisphere. The asymmetry puzzles you slightly, each hemisphere developing its own patterns despite experiencing similar physical conditions. The atmosphere containing complexities that resist simple explanation. The ring system demands increasing attention as multiple distinct components separate from what appeared earlier as a single uniform disk. Gaps and divisions appear as dark lines, separating brighter regions from each other. The structure showing organization into discrete rings rather than a continuous sheet. The most prominent gap shows as a dark band separating the outer A ring from the broader B ring. This Cassini Division, marking a region where particles cannot maintain stable orbits. The rings appear brightest where they catch direct sunlight on their faces. Billions of ice particles collectively reflecting light so efficiently that the rings sometimes look as bright as the planet itself. You find the rings drawing your eye repeatedly, their presence transforming Saturn from merely another giant planet into something visually unique. The temperature reading for Saturn's cloud tops displays minus 180 degrees Celsius, cold enough to freeze carbon dioxide solid, and cold enough that methane and ammonia condense into ice crystals. The extreme cold results from Saturn's distance from the Sun, combined with the lack of any solid surface to retain heat. The upper atmosphere continuously radiating thermal energy into space while receiving minimal solar input. The cloud deck you observe represents only the uppermost layer of an atmospheric structure extending thousands of kilometers downward, temperature rising steadily with depth as gravitational compression heats the gas. You know these facts from the mission briefing, but seeing the pale frozen clouds directly gives the knowledge different weight. The spacecraft's trajectory curves slightly as Saturn's gravity strengthens with proximity, the planet's pull now dominating over the Sun's influence on your vessel's motion. The navigation display confirms capture into the Saturnian system, Saturn's gravity controlling your orbital dynamics from this point forward. The final approach phase has begun, and you orient the spacecraft for passage through the ring system, checking the trajectory that will carry you through the outer ring structures before you reach the planet itself. The rings extend from just above Saturn's cloud tops outward to more than twice the planet's radius, confined to a disk only tens of meters thick, despite enormous horizontal extent. Your route will thread through that thin plane at a location calculated to minimize collision risk. The pale golden globe continues expanding in your view, atmospheric features growing clearer, and you notice bright and dark patches marking individual storm systems embedded in the overall banded structure. Some storms appear as small, bright ovals, where convection brings material upward from deeper levels, while others show as darker regions, where descending gas allows views into warmer atmospheric layers. The atmosphere consists primarily of hydrogen and helium. these two lightest elements dominating Saturn's composition, with trace amounts of methane, ammonia, water vapor, and other compounds contributing to the clouds and coloring. You recall the composition data from your training, but watching the actual clouds move and evolve across the face of a real world makes the abstract percentages feel concrete. Saturn and its rings appear surprisingly bright despite the weak sunlight. At this distance, the high reflectivity of the cloud tops and ring particles compensating for reduced solar illumination. The ammonia ice crystals forming the upper clouds bounce roughly half the incoming sunlight back into space, creating sufficient reflected light that observation remains clear even with solar intensity reduced to 1% of Earth's value. The view needs some enhancement from the spacecraft's visual systems, exposure times lengthened to gather enough photons for clear images. But the result shows features that would appear only dimly to completely unaided human eyes. Particle detectors begin registering occasional impacts as the spacecraft approaches the outer edge of the E-ring, Saturn's most extensive ring structure. Though nothing changes through the windows to indicate you have entered any new region, the E-ring extends across an enormous volume, reaching from well inside one moon's orbit outward beyond another moon farther out, spanning hundreds of thousands of kilometers in a shape centered on Saturn's equator. The particles spread so thinly through this vast space that density remains barely above vacuum, the detection equipment confirming their presence, while your eyes see nothing different. You glance at the detector readout occasionally, watching the impact rate climb slowly, but mostly you keep your attention on the view ahead where Saturn fills the windows. The giant golden world shows its atmospheric patterns clearly now. Delicate banding across its face, the rings stretching outward in a broad, bright structure, and your trajectory aims directly toward that ring system. The approach phase transitions into the ring passage phase as you prepare to enter Saturn's ring system properly, beginning with the sparse outer rings before penetrating the denser main structures closer to the planet. You check the spacecraft systems one more time, confirming shield integrity and trajectory parameters, then settle back to watch the final approach. The journey through the Saturnian system begins in earnest within the next hours as you enter the outer rings and start moving through the structures that circle this giant world. The detector panel shows increasing particle counts as you travel deeper into the E-ring, impact rates climbing from occasional hits to several per second. Though the view through the windows still shows nothing obviously different from empty space. The E-ring particles measure mostly less than 1 micrometer across, essentially smoke-sized ice grains that your eyes cannot see individually, but which surround the spacecraft in low concentration. You find it strange to know you are traveling through a ring while seeing nothing to indicate its presence. The space ahead looks as star-filled and empty as it did before you crossed the E-ring boundary, Saturn hanging in the darkness ahead just as it has for days now, growing steadily larger. Enceladus appears as a small bright point moving against the background stars, its position marking where the E-ring reaches its highest density. The Moon continuously ejects water ice into space through geysers erupting from fractures near its south pole, material escaping the small Moon's weak gravity and entering orbit around Saturn. The geysers shoot plumes, hundreds of kilometers above Enceladus's surface. Fresh ice constantly replenishing the E-ring as older particles slowly spiral away. You watch Enceladus for a while, the moon too distant to show as more than a point. But knowing what happens there makes that point of light seem more active than the static stars around it. This entire ring you are traveling through came from that small world. Billions of tiny ice particles launched into space over millions of years. Occasionally, your eye catches a brief flash through the window as an individual particle tumbles past, close enough and at the right angle to reflect sunlight directly toward you. The ice surface glints for an instant before the particle's rotation carries the reflective face away, and it vanishes back into invisibility against the stars. These occasional flashes remind you that countless ice grains surround you despite their invisibility to casual observation, each particle following its own orbital path around Saturn. You start watching for the flashes deliberately, counting them, trying to estimate how many particles might occupy the space around you, based on how frequently you spot one catching sunlight. The calculation proves impossible with so many unknowns, but the attempt keeps you engaged during the hours of E-ring transit. The particles out here drift through cold darkness, temperatures dropping well below -150 degrees Celsius, according to the external sensors. Each ice grain achieves balance between the faint solar radiation it absorbs and the infrared thermal radiation it emits, settling at temperatures where water ice remains stable indefinitely without sublimating. The particles follow elliptical paths, determined by their positions and velocities when they left Enceladus. Gravitational tugs from Saturn's moons gradually changing each particle's trajectory over months and years. Some particles eventually spiral inward towards Saturn, while others drift outward and escape the ring entirely. But the continuous supply from Enceladus maintains the overall population despite these losses. Hours pass as the spacecraft continues inward through the E-ring's broad volume. Your trajectory carrying you gradually closer to Saturn, while traversing the region where Enceladus's ejecta spreads through space. The passage takes time due to the ring's enormous extent, despite your substantial velocity, and you spend much of it simply watching Saturn grow through the forward window. The planet looks noticeably larger than it did when you entered the E-ring. Atmospheric features showing more structure, individual cloud systems visible within the broader zones and belts. The hexagonal polar structure shows remarkable detail now, the straight edges and sharp corners clearly defined, smaller features visible within the hexagon's area. The South Polar region displays its cyclonic system, with spiral cloud bands wrapping around the southern storm in patterns that grow more apparent as distance decreases. The F-ring appears ahead as a bright, narrow line against the darkness beyond Saturn's limb, standing out clearly even from thousands of kilometers away. The narrow band looks almost solid compared to the invisible particle haze of the E-ring environment, its concentration and brightness far exceeding anything you have encountered so far. As you close on the F-ring over the next hours, structure appears along its length, the simple bright line resolving into something more complex. Braids, kinks, and clumps distribute themselves along the ring's circumference, the pattern showing organization beyond a simple uniform band. The ring maintains a width of only a few hundred kilometers, despite orbiting at 140,000 kilometers from Saturn's center. The narrowness immediately suggesting that something confines the particles against their natural tendency to spread. Two faint points of light move near the F-ring as your spacecraft approaches to within tens of thousands of kilometers, and you consult the navigation display to confirm their identities. Prometheus and Pandora, the shepherd moons, orbit just inside and outside the F-ring respectively. Prometheus moves slightly faster in its interior orbit, periodically overtaking sections of the ring and gravitationally disturbing the particles during each passage. Pandora orbits more slowly in its exterior position, sections of the ring catching up to it and experiencing similar gravitational perturbations. The two shepherds work together to confine ring material between their orbits, stealing orbital energy from particles attempting to drift outward and adding energy to particles drifting inward. You watch the moons for a while, tracking their slow motion relative to the F-ring, imagining the gravitational dance playing out over orbital periods. The F-ring structure shows increasing complexity as you approach close enough to observe details smaller than hundreds of kilometers across. In some sections, the ring appears braided, multiple strands winding around each other in helical patterns that shift position along the ring's length. Bright clumps interrupt the overall structure at irregular intervals, regions where particle concentration temporarily increases above the surrounding density. These clumps likely mark locations of small moonlets embedded within the ring, whose gravity pulls material into temporary concentrations. You compare the current view against images captured hours earlier during approach, and notice the structure has changed perceptibly, features evolving on timescales of hours to days as particles respond to gravitational perturbations. The F-ring looks active, dynamic, nothing like a static structure. Your spacecraft passes within a few thousand kilometers of the F-ring, close enough that individual larger particles separate from the collective glow. The ring material reveals itself as countless discrete ice chunks rather than a continuous structure, particles ranging from invisible dust up to boulders several meters across. The larger chunks show as distinct bright points catching sunlight, each object tumbling slowly as it orbits Saturn and creating variations in brightness as different faces rotate into view. Sunlight, reflecting from thousands of visible particles, creates a glittering appearance, individual flashes combining into an overall sparkle that runs along the ring's length. The visual effect differs completely from the smooth glow visible from greater distance, where individual particles blend together. This close view, showing the ring's true nature as a swarm of separate orbiting objects. Collisions happen frequently in the denser clumps you suspect, though at these relative velocities, the impacts would appear gentle rather than violent. Small debris clouds surround some of the larger clumps, fine material created by recent collisions, not yet dispersed by orbital dynamics. The dust contributing disproportionately to the ring's brightness through its efficient scattering of sunlight. The collision rate here far exceeds that in the sparse E-ring. The F-ring's higher particle density and narrow confinement, bringing particles close enough together that impacts must occur regularly. The collisional grinding continuously reshapes the size distribution, and creates the observed mix of sizes from boulders to dust, larger particles slowly fragmenting into smaller ones over time. Your trajectory carries you past the F-ring and into the gap between that narrow structure and the outer edge of the A-ring visible ahead. The gap appears notably emptier than the F-ring just passed. The space here swept relatively clear by orbital resonances and gravitational perturbations from nearby moons. Crossing this gap takes only minutes at your current velocity, the spacecraft transitioning from the realm of narrow, shepherded rings to the broad, dense structures that define Saturn's appearance from Earth. You take the opportunity during the gap crossing to check systems and prepare for entry into the main rings, the particle environment about to change dramatically. The A-ring's outer edge approaches rapidly, visible as a sharp boundary where brightness suddenly increases. The transition from the nearly empty gap to the dense main ring occurs across only a few kilometers, the boundary appearing almost like a wall in space ahead. The detector readouts climb sharply as you near the boundary, impact flux increasing from occasional hits to hundreds per second. The A-ring extends inward from this outer edge across thousands of kilometers of radial distance, containing far more total mass than all the outer rings combined. Billions of ice particles, ranging from dust to house-sized chunks, orbit together in a flat disk, only tens of meters thick, vertically, but vast, horizontally. You brace slightly as the spacecraft crosses the boundary, an instinctive reaction, despite knowing the shielding handles these particles easily. The environment transforms the instant you cross into the A-ring, the view through the windows changing from relatively clear space to a region visibly filled with particles, extending in all directions, parallel to the ring plane. Looking towards Saturn shows countless ice chunks between your position and the planet beyond. The particle-filled view, quite different from the clear line of sight available in the outer regions. Particles near the spacecraft show as individual distinct objects, their sizes and shapes visible, surfaces catching sunlight as they tumble in their orbits. More distant particles blend into a collective glow that creates the overall brightness characteristic of the main rings. You find yourself turning to look outward along the ring plane, seeing the vast, flat sheet of orbiting ice extending to either side, the structure's thinness apparent from your position within it. The ice looks bright white where fresh surfaces reflect sunlight cleanly, though some chunks show subtle darker coloring where contamination from rocky dust or organic compounds mars the pure water ice. These color variations create subtle differences visible between different particles drifting past your window. Some pieces brilliant white, while others show faint browns or grays. Water ice dominates the composition throughout the A-ring, the spectral signature confirming what the visual appearance suggests. Temperature readings show the particles maintaining minus 180 degrees Celsius or colder, the ice remaining frozen solid at these temperatures, despite the name ice, sometimes suggesting something less permanent. Particles nearest the spacecraft show details you could not observe from farther away. Irregular shapes marking most chunks rather than smooth spheres. The surfaces showing texture from impacts and fragmentation events. Some pieces appear almost fluffy, their surfaces covered in what looks like frost or loose ice grains, adhering to the main body. Others show cleaner surfaces with smoother faces, where recent fractures exposed fresh ice. The chunks tumble in various orientations, their rotation rates varying from piece to piece, some spinning noticeably during the seconds they remain visible near the window, while others barely rotate at all. You watch the parade of ice chunks drifting past, each one unique, their collective motion creating the ring structure visible from outside. The view outward along the ring plane extends for thousands of kilometers before distance and particle density combine to obscure the view. The vast sheet of orbiting material stretching further than you can see. The ring plane extends to either side as a glowing band, brighter in some directions where particle density runs higher and dimmer in others, where gaps or divisions reduce the concentration. Above and below the ring plane, the view opens to clear space and stars, the ring's thinness creating a sharp boundary between the particle-filled plane and the empty space perpendicular to it. You appreciate the geometry directly in a way that external images never quite conveyed. The ring, truly a two-dimensional structure, embedded in three-dimensional space. The spacecraft continues inward, across the A-ring toward the Cassini Division and the B-ring beyond. The shielding handling particle impacts smoothly as designed. Small ice grains vaporize against the reinforced surfaces. Without causing damage, the vessel, built specifically to survive passage through this environment. The journey through the ring system proceeds according to plan, bringing you steadily closer to Saturn's cloud tops, visible through the particles ahead. Once clear of the rings, you will begin atmospheric entry and the descent through Saturn's interior. But for now, you travel through this field of orbiting ice, watching the particles drift past the windows, the main rings proving even more spectacular from within than they appeared from outside. The spacecraft crosses the boundary into the A-ring, and the environment around you transforms immediately from the relative emptiness of the gap region into a zone filled with orbiting ice particles, visible in every direction. Chunks of ice ranging from pebbles to boulders drift past in their individual orbits, each piece tumbling slowly as it circles Saturn, the surfaces catching sunlight and reflecting it in brief flashes before rotation carries the bright face away into shadow. The particle density here far exceeds anything you encountered in the outer rings. The separation between neighboring chunks measuring in meters or tens of meters rather than kilometers. The space around your spacecraft now genuinely crowded with orbiting material. The collective mass of these billions of particles creates the bright appearance of the A-ring when observed from outside. But from within the ring, you experience it as a three-dimensional cloud of objects extending to either side along the ring plane, while remaining confined to a remarkably thin vertical layer. The thinness of the ring becomes apparent as you observe the distribution of particles around you. The material concentrated into a layer typically 10 to 20 meters thick, while the ring extends hundreds of thousands of kilometers horizontally. The ratio of thickness to width, comparable to a sheet of paper scaled to the size of a large city. This extreme flatness results from the tendency of orbiting particles to collide and exchange momentum. Any particle whose orbit carries it above or below the main ring plane, eventually colliding with particles in the plane and having its vertical motion dampened through the impact. Over millions of years, these collisions have flattened the ring into the minimum possible thickness, a disk lying precisely in Saturn's equatorial plane, where the gravitational field creates stable circular orbits. Occasional particles drift above or below this thin layer, their orbits temporarily carrying them out of the plane until the next collision returns them to the main sheet. But the vast majority of ring material remains confined to the flat disk you are traversing. The ice particles around you show variety in size and shape, the population spanning from dust grains, barely visible through your spacecraft's windows, up to irregularly shaped chunks several meters across, each piece representing a fragment broken from larger objects through countless collisions over the ring's history. Most particles appear roughly spherical or rounded from repeated impacts that chip away sharp edges, though some larger pieces retain irregular shapes, suggesting they fragmented relatively recently from bigger parent objects. The surfaces show textures ranging from smooth, where ice has been polished by impacts with smaller particles, to rough and craggy, where fresh fractures exposed new material. The collision history of each particle, written in its surface characteristics. Colors range from pure white for clean water ice to slight gray or tan tints, where dust and organic compounds contaminate the ice. The color variations creating subtle patterns when you observe large numbers of particles together. The particles orbit Saturn independently, each following an elliptical path determined by its position and velocity. Though most orbits remain nearly circular and differ from neighboring particles' orbits by only tiny amounts. This similarity in orbital parameters means that relative velocities between nearby particles stay low. Collisions happening at speeds of centimeters or meters per second, rather than the kilometers per second that would result if orbits differed greatly. The gentle collision speeds allow particles to survive impacts without shattering, the ice absorbing the impact energy through slight compression and fracturing rather than catastrophic breakup. Though over time, the repeated impacts do grind larger particles down into smaller ones and create the dust that fills the gaps between bigger chunks. You witness several collisions as particles drift together and touch, the contacts appearing almost delicate, the pieces bouncing apart slowly or tumbling together for a moment before separating and continuing their individual orbits. Looking towards Saturn through the ring plane gives you a clear view of the planet's atmosphere beyond the inner ring edge, the cloud tops visible through the gaps between orbiting particles, the view alternately blocked and revealed as ice chunks drift across your line of sight. The ring casts shadows onto Saturn's cloud tops, dark bands stretching across the planet's face, where the ring material blocks sunlight from reaching the atmosphere below. The shadows moving slowly as Saturn rotates beneath its rings, while the rings themselves orbit at their own rate. The shadows appear darkest where the ring reaches highest particle density and become fainter where the ring thins, creating patterns that reveal ring structure through the shadows they cast. Looking away from Saturn shows you the outer edges of the ring system and the darkness of space beyond. Stars visible through the ring material, except where particle density becomes high enough to block the view completely. The Cassini Division appears ahead as a gap in the particle distribution, a region several thousand kilometers wide, where the density drops dramatically compared to the bright A and B rings on either side. The division represents a zone cleared by orbital resonance with Saturn's moon Mimas, which orbits far outside the rings, but whose gravitational influence reaches inward through orbital mechanics to affect ring particles at specific distances. Particles orbiting in the Cassini Division location complete exactly 2 orbits for every 1 orbit of mass. And this 2-to-1 resonance creates periodic gravitational tugs that add up over time and pump energy into the particle's orbits until they drift away from the resonance location. The clearing process has swept most material out of the division, though faint ringlets remain within it, narrow bands of material that avoid the resonance through slight orbital differences and persist in the partially cleared gap. Entering the Cassini Division feels like emerging from a dense cloud into clearer space, the particle density dropping suddenly as you cross from the A ring into the division. The crowded environment giving way to sparser distribution, more similar to the outer rings you traversed earlier. The division extends across your trajectory for thousands of kilometers, a surprisingly wide gap, considering the narrow rings and divisions elsewhere in the system. The cleared zone, wide enough that Saturn appears much more clearly through the reduced particle concentration. Several faint ringlets cross the division as thin bands of material, each ringlet containing its own population of particles, orbiting together in narrow zones that somehow avoid the resonance effects that cleared the surrounding regions. The ringlets appear as subtle concentrations against the generally empty division, their presence revealing that ring dynamics involves more complexity than simple resonance clearing. Small variations in orbital parameters, creating zones where particles can survive, even within generally cleared regions. The B-ring boundary approaches as you cross the inner edge of the Cassini Division, and the particle density increases again, but this time to values exceeding even the A ring's concentration. The B ring, representing the densest and most massive component of Saturn's entire ring system. Particles pack together so closely here that the ring becomes nearly opaque, sunlight unable to penetrate through the thickness of the material. The collective reflection from the densely packed ice, creating the brightest part of the ring system visible from Earth. The environment around you becomes intensely crowded with ice chunks, separations between particles shrinking to mere meters in many regions. The spacecraft's navigation systems working continuously to avoid larger chunks while accepting that impacts from smaller particles become inevitable in this dense zone. The B ring extends across tens of thousands of kilometers, a broad zone of high particle density that contains more mass than all other ring components combined. The sheer quantity of material here dominating the ring system's total inventory. The thickness remains similar to other rings, confined to a few tens of meters vertically, despite the high density. The same collision-based flattening process, operating here as everywhere else in the ring system. The particles show similar characteristics to those in the A ring. Water ice chunks ranging across sizes from dust to boulders, though the size distribution may differ slightly, with the B ring containing somewhat more mass in mid-sized particles. The brightness around you becomes striking when the sun angle allows direct reflection. Billions of ice surfaces, bouncing sunlight efficiently, the collective glow creating illumination levels that reduce the darkness of space significantly within the dense ring environment. The opacity of the B ring means that looking towards Saturn shows you only the nearest particles rather than a view through to the planet. The accumulated material, blocking sight lines longer than a few hundred meters in most directions, your view hemmed in by the crowded ice environment. Looking perpendicular to the ring plane, either toward Saturn's north or south pole, opens up clear views since that direction takes you out of the ring material within a few tens of meters. The extreme thinness of the ring, evident in the contrast between blocked views along the ring plane and open views perpendicular to it. This disorienting environment, crowded horizontally but open vertically, creates unusual visual impressions as you navigate through the B ring's densest zones. Temperature measurements continue showing extremely cold values. The ice particles maintaining temperatures around -180 degrees Celsius, the same as the cloud tops you will eventually reach after passing through the ring system. The particles radiate thermal energy into space as infrared light, while absorbing minimal solar heating, the equilibrium temperature settling at values where water ice remains stable across billions of years. Some particles in the B ring's densest regions may be shielded from direct sunlight by surrounding particles. These shadowed chunks potentially reaching even colder temperatures than their sunlit neighbors, though the differences remain small, and all particles maintain temperatures far below the freezing point of water. Collisions happen frequently in the B ring, the high particle density ensuring that chunks interact regularly as their orbits carry them past each other at slow relative velocities. You observe impacts occurring around you, particles touching and bouncing apart. The exchanges of momentum subtle but continuous throughout the ring's volume. The collision process, gradually redistributing orbital energy among the particle population. These collisions produce the dust that fills spaces between larger chunks, each impact chipping tiny fragments from the participants, the fragments themselves becoming new particles that orbit independently and contribute to the ring's overall optical properties. Over time, the collisions grind down the largest particles, while the smallest dust grains spiral inward towards Saturn, or become electrically charged and drift away. The size distribution maintained in a dynamic equilibrium between fragmentation creating small particles and various loss mechanisms removing them. The spacecraft continues its traverse through the B ring, thousands of kilometers of dense particle environment passing around you as the trajectory carries you steadily inward toward the inner rings and eventually towards Saturn itself. The B ring represents the heart of the ring system, the largest concentration of material and the most visually prominent component. The structure that makes Saturn immediately recognizable in images from across the solar system. Passing through this dense zone gives you direct experience of what it means to travel through a planetary ring. The environment, utterly unlike empty space, but also unlike any atmosphere or solid surface. A unique regime where billions of independent objects share similar orbits and create collective structures visible across millions of kilometers. The inner edge of the B ring approaches gradually as particle density begins decreasing. The transition to the C ring happening across a boundary less sharp than the Cassini Division, but still noticeable as the crowded B ring environment gives way to the more transparent C ring zone. The C ring appears darker and fainter than the A and B rings. Its lower particle density and possibly different size distribution, making it less reflective despite containing substantial material. The transparency returns to your view of Saturn, the planet's cloud tops becoming visible again through the C ring material, the view improving as you progressively less dense regions. The C ring extends inward from the B ring toward the planet itself, its inner edge approaching the top of Saturn's atmosphere, where the ring system finally ends and atmospheric gas begins. The transition from ring environment to atmospheric environment, waiting ahead as the next phase of your journey. The ring particles here orbit at higher velocities than those in the outer rings, the stronger gravitational pull at smaller orbital radius, requiring faster motion to maintain stable orbits. The innermost ring particles completing their circuits around Saturn in just a few hours. Your trajectory will carry you through the sea ring's inner edge and then beyond the ring system entirely, leaving behind the environment of orbiting ice particles and entering the realm of Saturn's atmosphere, where gas, rather than solid chunks, dominates, where the journey transitions from passage through rings to descent into the giant planet itself. Your spacecraft passes beyond the inner edge of the sea ring, leaving the last orbiting ice particles behind as your trajectory carries you across the gap between ring system and atmosphere, a zone several thousand kilometers wide where neither ring material nor atmospheric gas exists in significant quantities. The view ahead shows Saturn's cloud tops curving away below, the golden atmospheric surface now appearing closer than it did from your initial observation position outside the rings. The planet's curvature more apparent from this reduced distance. The rings behind you remain visible as a bright band stretching across the sky. The structures you traveled through now displayed from a new perspective, the flat disk seen edge-on, showing the different rings as concentric zones of varying brightness. The transition from ring environment to atmospheric environment happens gradually rather than abruptly. The spacecraft, first encountering individual atmospheric atoms drifting in near vacuum conditions, before gas density builds to values that constitute a measurable atmosphere. The exosphere begins first, the outermost atmospheric layer where gas particles exist so sparsely that they rarely collide with each other. Each hydrogen or helium atom, following a ballistic trajectory, influenced primarily by Saturn's gravity, rather than by interactions with other atoms. The density measures only a few hundred atoms per cubic centimeter, conditions barely distinguishable from the vacuum of space. The transition from no atmosphere to exosphere, almost imperceptible except through sensitive instruments that detect the gradually increasing particle counts. These exospheric atoms have sufficient thermal velocity that some escape Saturn's gravity entirely, the lightest and fastest atoms reaching escape velocity and drifting away into interplanetary space. The planet slowly losing atmospheric gas through this thermal escape process, though the loss rate remains negligible compared to Saturn's enormous atmospheric mass. The atoms around you consist primarily of hydrogen, the lightest element and the most abundant in Saturn's composition, with helium comprising most of the remainder and trace amounts of other elements present in tiny quantities. The hydrogen exists as individual atoms in the exosphere rather than the H2 molecules that dominate at lower altitudes. Solar ultraviolet radiation having broken many molecules apart at these heights where the thin atmosphere offers little shielding from incoming photons. The individual atoms drift in straight-line paths until they collide with another atom or until gravity curves their trajectory back downward into denser atmospheric layers, the ballistic motion creating a tenuous gas envelope extending thousands of kilometers above the level where the atmosphere becomes thick enough for frequent collisions. Temperature measurements show paradoxically high values despite the extreme cold you might expect in the outer reaches of Saturn's atmosphere. The exospheric atoms possessing kinetic energies corresponding to temperatures of several hundred degrees Kelvin, even though the actual heat content of the gas remains negligible due to the extremely low density. This temperature reflects the high velocities of individual atoms, rather than any substantial heat capacity. The sparse gas, unable to warm or cool objects passing through it, despite the atom's individual speeds. The high kinetic energies result from solar ultraviolet radiation, energizing the atoms, the photons transferring momentum and energy to the atmospheric particles and maintaining the hot sparse gas at high altitudes. Descending deeper brings increasing atmospheric density as you enter the thermosphere, the layer below the exosphere, where collisions between atoms begin happening frequently enough to establish thermal equilibrium and allow conventional temperature measurements. The thermosphere extends downward from altitudes around 1,000 kilometers above the reference level to perhaps 300 kilometers, a zone where density increases steadily with decreasing altitude, while temperature paradoxically remains high or even increases with depth. The temperature behavior results from absorption of solar ultraviolet radiation by the sparse gas, the incoming photons exciting and ionizing atmospheric atoms and transferring energy that manifests as heat. The heating most effective at altitudes where atmospheric density reaches values capable of absorbing significant solar energy, while remaining low enough that radiative cooling stays inefficient. The spacecraft begins experiencing measurable atmospheric drag for the first time, as the thermosphere's density builds to values where friction against the thin gas creates noticeable force on your vehicle. The control systems compensating with small thruster adjustments to maintain trajectory. The drag remains minimal compared to what you will encounter deeper in the atmosphere, but its presence signals the transition from orbital mechanics, where gravitational forces dominate motion, to aerodynamic flight, where atmospheric forces become significant factors in trajectory control. The thin gas streams past your spacecraft's surfaces, individual atoms striking the hull and bouncing away, each collision transferring tiny amounts of momentum that accumulate across millions of impacts per second to create measurable force. The magnetic field lines threading through the upper atmosphere channel charged particles from the solar wind towards Saturn's polar regions, the field geometry funneling electrons and ions downward along field lines that converge near the magnetic poles. These charged particles strike atmospheric atoms and molecules in the thermosphere and upper stratosphere, the collisions exciting the atmospheric species and causing them to emit light as aurora, glowing curtains and patches visible in ultraviolet wavelengths. Your instruments detect the aurora near the north and south poles, the emissions appearing as bright regions in ultraviolet images, even though the visible light aurora remains too faint to see with unaided human eyes from this distance and lighting condition. The auroral displays result from the same basic process that creates Earth's aurora, though the details differ due to Saturn's different magnetic field structure and atmospheric composition. Hydrogen emission dominates the auroral spectrum, the excited hydrogen atoms radiating characteristic wavelengths as electrons drop between energy levels. The ultraviolet glow marking locations where solar wind particles penetrate deepest into the atmosphere. The aurora intensifies and shifts location in response to changing solar wind conditions. The interaction between the stream of charged particles from the Sun and Saturn's magnetic field, creating dynamic behavior that varies on timescales from minutes to hours as the solar wind buffets the magnetosphere. Temperature begins declining as you descend through the lower thermosphere toward the stratosphere, the altitude where ultraviolet absorption becomes less dominant. and radiative cooling balances or exceeds solar heating. The atmospheric temperature dropping from the thermosphere's several hundred Kelvin toward the much colder values characteristic of Saturn's middle and lower atmosphere. The transition happens gradually across an altitude range where both heating and cooling processes operate, the temperature profile showing a gentle downward slope before flattening out in the stratosphere proper. The gas density continues increasing steadily with decreasing altitude, more atmosphere lying above you as you descend and pressing down through its weight. Each layer compressed by the layers above it, creating the exponential density increase that characterizes planetary atmospheres. The stratosphere extends from roughly 200 kilometers altitude down to the cloud tops at what defines the zero reference level. A thick layer where temperature stays relatively constant or increases slightly with depth. Ultraviolet absorption by methane and other hydrocarbons, providing some heating while the atmosphere remains too thin and cold for the convective processes that dominate at lower levels. The gas remains hydrogen and helium dominated throughout, but trace species like methane become important for atmospheric chemistry and energy balance, despite their small concentrations. Methane absorbs ultraviolet light and some infrared wavelengths, affecting both the heating rate and the spectrum of light that penetrates to deeper levels. The molecule's presence contributing to Saturn's characteristic color by absorbing red light preferentially. Haze layers begin appearing as you descend through the stratosphere. Thin concentrations of photochemical smog, created when ultraviolet light breaks apart methane molecules, and the fragments recombine into complex organic compounds that condense into tiny particles. These haze particles scatter sunlight and create subtle opacity that increases toward lower altitudes where particle concentrations build higher. The stratosphere taking on a slight haziness that contrasts with the nearly transparent conditions of the thermosphere above. The hazes appear as delicate layers when you observe them from certain angles, the scattering of sunlight revealing the vertical structure of particle distributions. Different haze layers existing at different altitudes where temperature and chemistry favor formation of specific compounds. Cloud tops become visible below as you approach the tropopause, the boundary between stratosphere and troposphere, where temperature stops increasing with depth and begins declining again. The altitude at which condensable vapors can form the first clouds of ammonia ice that create Saturn's visible atmospheric surface. The transition from the relatively clear stratosphere to the cloudy troposphere marks your passage from the upper atmosphere, which remains relatively inactive and stable, into the weather layer where convection and atmospheric dynamics create the zones and belts and storms visible from space. The pressure builds toward 1 bar, the pressure familiar from Earth's sea level. The altitude, defined as the zero reference level for Saturn's atmospheric measurements, despite no solid surface existing at this level or anywhere below. Light levels around you have remained relatively bright throughout the descent through the upper atmosphere, sunlight penetrating the thin gas with minimal absorption, the illumination comparable to the dimmed but substantial light you experienced in the ring system. The Sun appears small from Saturn's distance, a bright star rather than the large disk familiar from Earth's sky, but its light provides sufficient illumination to see clearly despite being 95% weaker than at Earth's distance. The pale gold coloring of Saturn's clouds becomes more apparent as you approach the cloud deck stretching across your view below. the bands and zones organized in parallel lines that circle the planet. The atmospheric structure you observed from outside, now waiting immediately beneath you. The spacecraft's trajectory steepens as you prepare for entry into the denser lower atmosphere. The descent path calculated to bring you through the cloud deck at an angle that manages heating from atmospheric friction while maintaining control during the transition from flight through tenuous upper atmosphere to flight through the thick tropospheric gas. The troposphere contains more than 99% of Saturn's atmospheric mass, despite representing a vertical extent of only a few hundred kilometers. The pressure increasing from 1 bar at the cloud tops to hundreds or thousands of bars at depths hundreds of kilometers below. Your journey will take you through those cloud layers and into the deep atmosphere, where pressure and temperature climb to values that transform hydrogen from molecular gas to liquid to exotic metallic states. The long descent to Saturn's core beginning in earnest as you pass through the cloud deck and enter the planet's interior regions. Temperature at the cloud top level measures around -180 degrees Celsius. Cold enough that ammonia vapor condenses into ice crystals that form the white clouds visible as bright zones in the atmospheric banding. The ice particles, creating the highest cloud layer and defining what observers perceive as Saturn's surface. Below this level lie warmer regions, where ammonium hydrosulfide clouds form at intermediate depths, and water clouds exist at the deepest tropospheric levels. The triple-layered cloud structure, common to gas giant atmospheres, representing condensation of different volatile compounds at different temperatures and pressures. The clouds organize themselves into zones and belts through atmospheric dynamics, driven by Saturn's internal heat and rotation. Rising gas creating cloud-covered zones, while sinking gas creates clearer, darker belts. The pattern maintained by jet streams flowing between the bands at velocities reaching hundreds of meters per second. The spacecraft enters Saturn's cloud layer, and the environment around you transforms from the relatively clear stratosphere into the hazy upper troposphere, where ammonia ice crystals begin forming the highest condensation clouds. Wispy structures drift past your windows, delicate ice particles suspended in the atmospheric flow, the ammonia frost creating white clouds that cluster into organized patterns, following the winds and convection cells operating at this level. The temperature sits around -180 degrees Celsius here, cold enough that ammonia vapor condenses readily despite its low atmospheric concentration. The ice crystals growing as water vapor does in Earth's clouds, but involving ammonia instead as the condensing species. The clouds appear thickest in the zones, the bright bands you observed from outside, where upwelling gas brings ammonia vapor from deeper, warmer levels into this cold region, where it freezes and forms extensive cloud decks. The banding structure becomes more apparent as you descend through the upper cloud layer, the zones and belts revealing themselves as regions with distinctly different vertical motion and cloud characteristics, rather than simple color variations. The zones represent areas where atmospheric gas rises from deeper levels, cooling as it ascends and expands into lower pressure. The cooling causing dissolved vapors to condense into clouds that obscure the deeper atmosphere and create bright reflective bands. The belts mark regions where gas descends back toward the interior, warming as it sinks and compresses into higher pressure, the warming causing clouds to evaporate and allowing you to see deeper, into darker atmospheric layers. This circulation creates the banded appearance, rising and sinking motion organized into alternating bands by Saturn's rotation. Through the Coriolis effect that deflects moving air into east-west flows rather than allowing simple north-south convection. Jet streams separate the zones and belts, narrow bands of extremely fast east or west wind flowing along the boundaries between rising and sinking regions. The wind speed reaching peak values at the interfaces where atmospheric dynamics concentrate momentum into focused streams. The jet streams appear as linear features when you observe cloud patterns from altitude. The sharp boundaries between zones and belts, maintained by the powerful winds that prevent mixing between the different atmospheric regimes. Wind velocities in the strongest jets exceed 400 meters per second at equatorial latitudes. The fastest winds in the solar system flowing through Saturn's atmosphere in organized bands that circle the planet, their speed far exceeding even Jupiter's powerful jets. The winds carry cloud material along at these tremendous velocities. The ammonia ice crystals embedded in the flow, streaming eastward or westward depending on latitude. The visual appearance of the clouds, showing the motion through streak patterns and wave structures. The hexagonal pattern at Saturn's north pole becomes visible in the cloud structures as you pass over northern latitudes during your descent. The geometric formation revealing itself as a standing wave in the jet stream that circles the pole at latitude 78 degrees north. The hexagon consists of 6 relatively straight segments connected by sharp corners, each side measuring longer than Earth's diameter, the entire pattern rotating around the pole, with a period matching Saturn's internal rotation rate, rather than following the winds at the cloud level. This peculiar structure represents a stable wave pattern in atmospheric flow, the dynamics somehow favoring sixfold symmetry at this particular latitude under Saturn's specific combination of rotation rate, atmospheric depth, and thermal structure. No other planet shows similar geometric atmospheric features. The hexagon, representing a unique configuration that has persisted for at least decades since its discovery in images from the Voyager missions in the early 1980s. The center of the hexagon contains a massive cyclonic storm, a vortex of clouds spiraling around the North Pole itself. The storm eye measuring roughly 2,000 kilometers across and surrounded by a wall of clouds where the strongest upward motion occurs. The cyclone resembles a hurricane in structure, with a clear central eye where air descends and warms, surrounded by spiraling bands where air rises and cools. Though the scale dwarfs any terrestrial storm, and the driving mechanisms differ with internal heat rather than ocean evaporation providing the energy, the storm appears to extend deep into the atmosphere, the vertical extent possibly reaching hundreds of kilometers from the cloud tops downward into regions where increasing pressure and temperature change the atmospheric structure. The cyclone representing not just a cloud feature, but a deep convective system threading through multiple atmospheric layers. Temperature increases gradually as you descend below the uppermost ammonia clouds into slightly warmer levels where gas temperature climbs from -180 toward -180 toward -50 degrees Celsius, the warming resulting from compression as the weight of atmosphere above presses down on deeper layers. Pressure similarly increases from the 1 bar level at the ammonia cloud tops toward 2 bars, 3 bars, higher values at progressively greater depths. each additional layer supporting the weight of all atmosphere above it, and compressing to higher density accordingly. The pressure increase follows an exponential pattern initially, roughly doubling for each scale height of depth, though the relationship becomes more complex deeper down, where temperature gradients and composition changes affect the atmospheric structure. The lower cloud decks appear below the ammonia layer, zones where other volatile compounds reach their condensation temperatures and form separate cloud layers at depths where human eyes can no longer penetrate from above. Ammonium hydrosulfide clouds condense at temperatures around -90 degrees Celsius, forming a second cloud deck some 50 kilometers below the ammonia layer. These clouds contributing brown and orange tints to the overall atmospheric appearance in regions where the upper ammonia clouds thin enough to allow light to reach these depths. Deeper still, water clouds form where temperature rises above -50 degrees Celsius. The water ice, or possibly liquid water droplets, creating a third cloud layer, another 50 kilometers down. The water clouds, representing the deepest condensation level in Saturn's troposphere, and the boundary where the observable atmosphere gives way to the deep interior regions that remain forever hidden from external view. Light begins fading as you descend through the cloud layers, the ammonia ice above you scattering and absorbing sunlight, reducing the illumination, reaching deeper levels to dimmer values than the bright conditions at the cloud tops. The sunlight that penetrates shifts toward orange and red wavelengths, the blue and green light scattered preferentially by the cloud particles above, leaving longer wavelengths to illuminate the deeper atmosphere. Below the ammonia clouds, the light continues dimming as you pass through the ammonium hydrosulfide layer, its particles adding more scattering and absorption, the illumination taking on deeper orange and brown tones as shorter wavelengths get filtered away. By the time you reach the water cloud level, sunlight has faded to twilight dimness, the thick cloud decks above blocking most direct solar radiation, the only light reaching these depths having scattered multiple times through the upper layers. Convection cells become apparent in the cloud structures around you, rising columns of warm gas, creating updrafts that carry water vapor and other species upward from deeper levels, while downdrafts between the updrafts return cooler gas to depth. These convection cells organize themselves into patterns that follow the overall zone and belt structure. Cells in the zones contributing to the net upward motion, while cells in the belts predominantly sink, but individual cells show complex three-dimensional structure as atmospheric parcels rise, cool, shed their condensable vapors as clouds, and then sink back down after losing their buoyancy. The convective motion transports heat from Saturn's interior toward the surface. The vertical mixing, carrying thermal energy upward more efficiently than radiation alone could manage. The convection process fundamental to how Saturn radiates its internal heat into space. Storm systems appear as discrete features embedded in the general cloud patterns, oval-shaped disturbances where particularly intense convection creates concentrated updrafts and rotation, the atmospheric equivalent of Earth's hurricanes, but powered by heat from below rather than surface evaporation. Some storms appear as bright white ovals where fresh ammonia ice clouds rise to high altitudes and reflect sunlight efficiently, while others show as dark ovals where descending air clears clouds and reveals deeper, darker atmospheric levels. The storms drift with the winds at their respective latitudes, carried along by the jet streams while maintaining their individual rotation and structure, some persisting for months or years before dissipating back into the general atmospheric flow. The Great White Spot phenomenon represents the largest and most energetic storm type on Saturn. Massive eruptions of convection that break through the normal cloud layers and create planet-girdling disturbances, visible even from Earth. These great storms appear roughly once per Saturn year, approximately every 30 Earth years, the timing suggesting some relationship between Saturn's seasons and the trigger conditions that allow the massive outbreaks. The storms start as bright white spots that rapidly expand and spread in longitude as the winds at different latitudes shear the storm material into long streamers that eventually encircle the planet. The fresh ammonia ice clouds rising from deep atmosphere, creating brilliant white features against the normally subtle cloud deck. Your descent path encounters only the normal, smaller storms and the everyday convection of Saturn's troposphere. The great storms being rare events that occupy a small fraction of time across Saturn's long seasonal cycle. Temperature continues rising as you descend past the water clouds into the deep troposphere below, the gas warming from the -50 degrees Celsius at the water cloud base towards 0 degrees Celsius, and then into positive temperatures at greater depths. The warming results from compression and from the heat flowing upward from Saturn's hot interior. The deep atmosphere receiving thermal energy from below that maintains temperatures higher than solar heating alone could achieve at Saturn's distance from the Sun. Pressure climbs past 10 bars at the water cloud level and increases toward dozens of bars as you continue downward. The atmospheric density becoming comparable to water, despite consisting of hydrogen and helium gas. The extreme pressure compressing the light elements to liquid-like densities, while they remain gaseous in molecular structure. Lightning flashes appear in the distance, electrical discharges occurring in the water clouds and in the deeper atmosphere below. The energy released during convective storms creating static charge separation that builds electric potential until breakdown occurs and current flows through discharge channels. The lightning on Saturn operates through the same basic physics that creates terrestrial lightning. Atmospheric motion, separating positive and negative charges until electrical forces overcome the insulating properties of the gas and current flows to neutralize the separation. But the scale exceeds Earth's lightning, with individual bolts extending across hundreds of kilometers. Radio emissions from the lightning appear as crackles and static. When detected by instruments, the electromagnetic pulses propagating through Saturn's atmosphere and escaping to space, where they were detected by spacecraft conducting remote observations from orbit. The spacecraft continues descending through the deep troposphere, leaving the illuminated cloud layers behind as you enter regions where sunlight never penetrates. The environment transitioning from the weather layer, with its visible clouds and solar-driven dynamics, into the deep interior where heat flow from below dominates and pressure begins reaching values that alter the fundamental nature of the hydrogen atmosphere. The troposphere extends downward to depths where temperature and pressure become high enough that the distinction between atmosphere and interior blurs. No sharp boundary separating gas from liquid or interior from atmosphere, just gradual transitions through progressively denser and hotter hydrogen and helium. Below lies the regime where molecular hydrogen begins giving way to atomic hydrogen under extreme pressure. And deeper still, the metallic hydrogen layer, where electrons separate from atoms entirely. These exotic states waiting ahead as your descent continues towards Saturn's core, thousands of kilometers below the cloud tops you have now left, far above. Darkness surrounds your spacecraft as you descend below the water clouds into regions where sunlight never reaches. The last scattered photons from above, absorbed by the thick cloud layers that now lie thousands of meters overhead. The only illumination comes from your vehicle's instruments and from the faint thermal glow of the atmosphere itself. The gas temperature rising into ranges where objects begin emitting infrared radiation, detectable by instruments sensitive to heat rather than visible light. The environment around you consists of hydrogen and helium gas compressed to densities approaching that of liquid water. The pressure now measuring dozens of bars and increasing steadily with each kilometer of descent. Each layer of atmosphere supporting the weight of all the gas above it through compression into progressively higher density. Temperature climbs past 0 degrees Celsius into the range of normal terrestrial temperatures. The deep atmosphere warm despite its great distance from the sun. The warmth coming from heat flowing upward from Saturn's interior, where gravitational compression and other energy sources maintain temperatures far exceeding anything solar radiation could produce. The gas behaves increasingly like a fluid as density builds toward liquid values. Though the molecules remain primarily in gaseous configuration, with hydrogen existing as H2 molecular pairs and helium as individual atoms. Viscosity increases with density, the atmosphere resisting flow more than thin gas at low pressure, the medium taking on qualities intermediate between normal gas and liquid, even though phase transitions have not yet occurred at these depths. Convection continues operating throughout this region, warm gas rising from deeper levels while cooler gas sinks back down, the vertical mixing transporting heat outward and maintaining the temperature gradient between hot interior and cold upper atmosphere. The convection cells extend across hundreds of kilometers horizontally and stretch vertically through the pressure levels you currently traverse. Your spacecraft passing through regions of updraft and downdraft as you descend through the organized convective pattern. Pressure increases past 100 bars, a value exceeding the deepest ocean trenches. On Earth, the weight of thousands of kilometers of hydrogen and helium above, pressing down on this deep atmospheric layer with force that would crush ordinary materials instantly. The hydrogen molecules withstand the pressure through the quantum mechanical properties that prevent atoms from occupying the same space. Electron shells around each nucleus, resisting further compression through the Pauli exclusion principle that forbids identical fermions from sharing quantum states. The gas can compress to densities approaching solid materials, while remaining gaseous because the molecules themselves resist being pushed closer together. The compression squeezing out empty space without destroying molecular structure at these pressure levels. Temperature reaches several hundred degrees Celsius as you descend toward depths where pressure approaches 1,000 bars. The heat content of the gas becoming substantial, even though no sunlight penetrates to these levels. The thermal energy stored in molecular motion representing heat flowing from deeper interior regions toward the surface. Saturn radiates more energy into space than it receives from the sun. the excess heat emission requiring internal energy sources to maintain. And you are now descending through regions where that internal heat becomes the dominant energy source rather than the solar input that drives the upper atmosphere. The heat flows outward through convection at these depths, gas circulation carrying thermal energy from hot, deep regions to cooler upper levels. Though radiation also contributes to energy transport, as the dense hot gas emits infrared photons that surrounding gas reabsorbs after traveling short distances. The source of Saturn's internal heat involves multiple contributions, the most significant being the slow gravitational contraction that occurs as the planet gradually shrinks over billions of years, converting gravitational potential energy into heat through compression of the interior. Additionally, helium may separate from hydrogen at certain depths and pressures within Saturn's interior. Helium droplets forming and sinking through the lighter hydrogen like rain, the falling droplets releasing gravitational potential energy that converts to heat and contributes to Saturn's excess luminosity. This helium rain hypothesis remains partially speculative, but provides a mechanism for ongoing heat generation beyond primordial heat left over from Saturn's formation. The separation and settling process potentially continuing throughout Saturn's lifetime and maintaining heat flow long after formation energy has dissipated. The composition remains overwhelmingly hydrogen and helium. Even at these depths, the atmosphere showing little enrichment in heavier elements compared to the solar composition that characterized the gas from which Saturn formed. Small quantities of water, methane, ammonia, and other compounds exist, dissolved in the hydrogen-helium matrix. Their presence detectable through spectroscopy and through the clouds they form at shallower depths. But these species contribute only a few percent to the total mass, even when combined. The simplicity of composition means that understanding Saturn's interior primarily involves understanding hydrogen behavior under extreme pressure and temperature, the properties of this simplest element determining most aspects of the planet's structure and evolution. Pressure reaches 1,000 bars as you descend past the level where molecular hydrogen begins experiencing stresses that affect molecular bonds. The compression and temperature starting to influence whether hydrogen atoms remain paired as H2 molecules or begin dissociating into individual atoms. The dissociation happens gradually over a range of depths, rather than at a sharp boundary, some molecules breaking apart, while others remain intact. The fraction of atomic hydrogen increasing with depth as pressure and temperature continue rising. The dissociation absorbs energy, each broken molecular bond requiring input of the binding energy that held the atoms together. This endothermic process affecting the temperature gradient by consuming some of the heat flowing upward from below. Density continues increasing as you descend, the hydrogen compressing to values around 0.5 gram per cubic centimeter, denser than many familiar liquids despite consisting of the lightest element, the extreme pressure forcing hydrogen into configurations never encountered in terrestrial environments. The material flows like a liquid and shows liquid-like density, but the individual molecules retain enough kinetic energy that the term gas remains applicable at some level. The distinction between liquid and gas becoming ambiguous under conditions far from those where the concepts were originally defined. Scientists sometimes use the term supercritical fluid to describe this state, A regime where temperature and pressure exceed the critical point beyond which liquid and gas phases no longer exist as distinct states. The material showing properties intermediate between the two familiar phases. Turbulence pervades the flow around you, the convection creating swirling eddies and vortices at all scales from meters to hundreds of kilometers. The atmospheric motion, organized into nested patterns of rising and sinking that transport heat and momentum throughout this deep layer. The largest scale convection cells span thousands of kilometers and organize into the zone and belt pattern visible at the cloud tops thousands of kilometers above, while smaller scale turbulence operates within the large-scale flow, creating complex three-dimensional motion throughout the volume. Your spacecraft experiences buffeting as it descends through regions of varying vertical velocity, updrafts and downdrafts creating forces that the control systems must compensate for continuously to maintain the planned trajectory. Temperature climbs past 1,000 degrees Celsius as you approach depths where pressure reaches several thousand bars. The gas now hot enough that it would glow visibly if light could propagate through the dense medium surrounding you, though in practice the mean free path for photons remains so short that radiation quickly thermalizes and contributes to the local heat content rather than escaping. The infrared glow that surrounds you represents thermal emission from the hot, dense hydrogen. Every volume element radiating according to its temperature, while simultaneously absorbing radiation from surrounding volumes. The energy exchange contributing to heat transport, even though no light escapes, to create visible illumination that your eyes could detect. Chemical reactions become possible at these elevated temperatures, despite the simple composition. Hydrogen and helium themselves remaining inert, but trace species undergoing transformations that alter their molecular forms. Methane begins breaking down into carbon and hydrogen, the carbon potentially forming more complex organic compounds or remaining as dispersed atoms, depending on local conditions. Ammonia similarly dissociates nitrogen and hydrogen atoms, separating and potentially recombining into other forms. Water remains relatively stable, but exists in forms quite unlike liquid water at Earth's surface. The high pressure and temperature creating dense fluid water that bears little resemblance to the familiar liquid, despite being chemically identical, H2O molecules. The deep troposphere extends across hundreds of kilometers of depth, the region defined by continuing convective instability that mixes gas vertically and maintains the connection between hot interior and cold upper atmosphere. Though the lower boundary of this zone becomes difficult to define precisely as conditions grade continuously into the deeper interior layers. Below lies the transition region, where molecular hydrogen gives way to atomic hydrogen, and where pressure increases past 10,000 bars toward the megabar values that force the phase transition to metallic hydrogen, that exotic state where hydrogen takes on electrical properties, resembling metals despite being compressed gas, composed of the simplest element. Your descent continues downward through progressively more extreme conditions, leaving behind the regime where atmospheric physics applies, and entering the domain of high-pressure physics, where matter behaves in ways that challenge our everyday intuitions about how materials respond to compression and heating. Velocity measurements show the gas around you still participating in organized east-west flows, even at these great depths. The rotation of Saturn extending deep into the interior and organizing motion into bands similar to those visible at the cloud tops. Though measurements of wind speed at these depths remain largely theoretical, inferred from models rather than direct observation. The zonal flows may extend downward until they reach levels where electrical conductivity becomes significant. The conducting fluid at those depths coupling to Saturn's magnetic field, which forces the material into corrotation with the planet's deep interior. The magnetic coupling eliminating differential rotation and enforcing uniform angular velocity at depths where metallic hydrogen begins. The spacecraft presses deeper into Saturn's interior. Thousands of kilometers of hydrogen now above you. Thousands more below, separating your current position from the possible rocky core at the planet's center. The journey has transitioned from atmospheric descent through clouds and weather into a descent through a deep ocean of hydrogen. The medium, dense, and hot and flowing in convection patterns that extend through vertical distances exceeding Earth's diameter. The environment alien to human experience, but governed by physical principles that apply universally throughout the cosmos. The pressure will continue building, the temperature will continue rising, and the hydrogen will undergo transformations that create states of matter unknown anywhere in the solar system, except in the interiors of giant planets. The spacecraft descends into regions where pressure climbs past 10,000 bars, 10,000 times the atmospheric pressure at Earth's sea level. The weight of the hydrogen and helium above, compressing this deep layer to densities that exceed liquid water, despite the material consisting of the lightest elements in the periodic table. Temperature reaches several thousand degrees Celsius at these depths. The gas hot enough that thermal energy approaches the binding energy of hydrogen molecules, the H2 pairs beginning to break apart under the combined assault of heat that makes molecules vibrate violently, and pressure that forces atoms closer together than molecular bonds prefer. The dissociation of hydrogen molecules happens progressively rather than at a single boundary, a fraction of molecules breaking into individual atoms, while the remainder stay paired, the proportion of atomic hydrogen increasing with depth, as pressure and temperature both rise toward values that favor dissociation. The transition from molecular to atomic hydrogen represents a significant change in the material's thermodynamic properties, the dissociation absorbing energy because molecular bonds must be broken. The endothermic process consuming heat that flows upward from below and affecting the temperature gradient through this transition zone. Each time an H2 molecule splits into two H atoms, the binding energy that held them together must be supplied by the surrounding thermal environment. This energy absorption cooling the gas slightly compared to what temperature would be reached through compression alone. The effect modifies the pressure-temperature profile through the dissociation zone, creating a region where temperature increases more slowly with depth than it does in layers above or below. The energy going into breaking bonds rather than into heating the material. Pressure continues increasing as you descend through the dissociation zone, reaching 20,000 bars, 30,000 bars, values far beyond anything achievable in terrestrial laboratories for more than microseconds. The conditions existing stably, here maintained by the enormous mass of Saturn pressing down from above. The hydrogen atoms, freed from their molecular partnerships, behave differently from H2 molecules, the individual atoms smaller and more mobile, their presence changing the viscosity and thermal conductivity of the mixture. Atomic hydrogen conducts heat more efficiently than molecular hydrogen under these conditions. The freed atoms transporting thermal energy through their motion more effectively than the larger molecules did. The transition to atomic form affecting how heat flows through this layer on its journey from the hot core toward the cold upper atmosphere. Density rises past the 1 gram per cubic centimeter threshold. The compressed hydrogen, now denser than liquid water at Earth's surface. An astonishing fact, given that hydrogen is 14 times lighter than oxygen atom for atom. And pure hydrogen gas, at normal pressure, weighs almost nothing. The extreme compression packs hydrogen nuclei and their electrons into configurations that occupy far less volume than the same atoms would require at low pressure. The material achieving metallic densities while still consisting fundamentally of hydrogen atoms held apart by electron clouds rather than forming the rigid structures characteristic of solid matter. The hydrogen flows continuously in convection currents. Despite its high density, the material behaving as a dense fluid rather than solidifying. The high temperature, maintaining enough thermal motion that atoms slip past each other easily, despite being pressed closely together. Helium remains mixed with hydrogen throughout the dissociation zone, in proportions roughly matching the solar composition, about 1 helium atom for every 10 hydrogen atoms. Though some models suggest helium may become less soluble in hydrogen under certain combinations of pressure and temperature encountered in Saturn's interior. If helium precipitation occurs, it would happen through a process where helium atoms cluster together and form droplets that separate from the hydrogen matrix. The denser helium then sinking through the lighter hydrogen, like rain falling through air. The falling helium droplets would release gravitational potential energy as they descend, this energy converting to heat and contributing to Saturn's observed excess thermal emission, the process providing a mechanism for ongoing heat generation billions of years after the planet's formation. The helium rain hypothesis remains difficult to confirm directly because observing Saturn's deep interior presents formidable challenges. No probe able to survive the pressures and temperatures long enough to measure conditions directly at these depths. And remote sensing techniques, unable to penetrate through thousands of kilometers of dense hydrogen to reveal what happens in the deep interior. Evidence comes from observations that Saturn appears depleted in helium compared to the solar composition. Measurements of the upper atmosphere showing less helium than expected if the primordial composition was preserved uniformly throughout the planet. The depletion suggests helium has settled toward the interior, separating from hydrogen and concentrating at depth, consistent with the precipitation hypothesis, though not proving it definitively. Temperature reaches 5,000 degrees Celsius as you descend toward the base of the dissociation zone. The hydrogen now predominantly atomic, rather than molecular. The gas consisting of individual H atoms, each surrounded by its electron cloud. The material hot and dense and flowing in convection patterns that transport heat and create the circulation connecting Saturn's interior to its visible atmosphere. The atoms collide frequently, exchanging momentum and energy. The frequent collisions establishing local thermal equilibrium and allowing temperature to be defined meaningfully despite the extreme conditions. The thermal energy represents kinetic motion of individual atoms. Their velocities, distributed according to the Maxwell-Boltzmann statistics that govern how energy distributes itself among particles in thermal equilibrium at any temperature. Pressure approaches 1 million bars, 1 megabar, the threshold where hydrogen undergoes another transition even more dramatic than molecular dissociation. The pressures becoming high enough that electrons begin behaving collectively rather than remaining bound to individual nuclei. The approaching transition to metallic hydrogen represents a fundamental change in material properties. The transformation from an electrically insulating atomic gas to a conducting metallic liquid happening as pressure squeezes atoms so closely together that electron orbits overlap and electrons delocalize across many nuclei rather than remaining associated with specific atoms. This transition creates the metallic hydrogen layer that occupies most of Saturn's interior volume. The conducting fluid that generates the planet's magnetic field through dynamo action when currents flow through the rotating conducting medium. The dissociation zone extends across a vertical distance of several thousand kilometers. The gradual transition from molecular to atomic hydrogen occupying a substantial fraction of Saturn's radius, the region where chemical bonds break and atomic physics begins dominating over molecular chemistry. The thermal structure through this zone reflects the energy absorption during dissociation, the temperature increasing more slowly with depth than in adjacent layers. The modification to the temperature profile, affecting convection patterns and heat transport throughout this region. Convection continues operating through the dissociation zone, atomic hydrogen rising where it becomes buoyant, through heating and sinking where cooling makes it denser than its surroundings. The circulation maintaining connection between the layers above and the exotic metallic hydrogen layer below. Your spacecraft's instruments measure the electrical conductivity of the surrounding hydrogen, detecting the increase as molecular hydrogen gives way to atomic form, and as the first signs of electron delocalization appear in the deepest regions you are currently traversing. Conductivity remains low compared to true metals at these depths, but it exceeds the effectively zero conductivity of molecular hydrogen higher up, the trend pointing toward the dramatic increase that will occur deeper down when the transition to metallic hydrogen completes. The increasing conductivity affects how the material interacts with Saturn's magnetic field. The field lines beginning to exert forces on currents flowing through the weakly conducting atomic hydrogen, though the coupling remains far weaker than it will become in the fully metallic regions below. The composition shows slight enrichment in heavier elements compared to the upper atmosphere. Water and methane and other compounds having a tendency to concentrate at depth, where higher pressure and different chemical potentials affect their distribution, though hydrogen and helium still dominate overwhelmingly, with all other elements combined, contributing only a few percent to the total mass. The heavy elements present may include not just gases, like water vapor and methane, but also dissolved rock and metals in forms completely unlike their familiar terrestrial appearances. Silicates and iron, potentially existing as individual atoms or small clusters, dispersed through the hydrogen matrix, rather than forming solid structures. The extreme conditions preventing formation of conventional mineral phases. Temperature, pressure, and density all continue their relentless increase as your descent carries you deeper into Saturn's interior, leaving behind the dissociation zone and approaching the metallic transition where the next major change in hydrogen's properties awaits. The environment has evolved from the cold, low-pressure clouds of the upper atmosphere through the warming, high-pressure, deep atmosphere and dissociation zone, each layer revealing new aspects of how matter behaves under progressively more extreme conditions. The journey demonstrating that planetary interiors contain physical regimes as exotic as any encountered elsewhere in the universe. Below lies the metallic hydrogen ocean, thousands of kilometers of electrically conducting fluid that will surround you as the descent continues toward the central regions where Saturn's possible rocky core waits at the end of this inward journey. Through every layer of the giant planet's structure, pressure surges past 1 million bars as your spacecraft enters the region where hydrogen undergoes its most dramatic transformation. The crushing force from thousands of kilometers of overlying material compressing the atomic hydrogen until electrons can no longer remain bound to individual nuclei. The atoms pack so closely together that electron clouds overlap. The quantum mechanical wave functions describing electron positions spreading across multiple nuclei rather than remaining localized around specific protons. The electron delocalization creating a state of matter fundamentally different from anything found naturally on Earth. This transition produces metallic hydrogen, a phase where electrons move freely through the material like conduction electrons in metals. The hydrogen taking on electrical and thermal properties resembling copper or aluminum, despite consisting solely of compressed hydrogen atoms with no other elements present. Temperature reaches 10,000 degrees Celsius at the depths where metallization begins. The combined extreme pressure and temperature forcing hydrogen into configurations impossible under normal conditions. The material entering a regime where experiments become extraordinarily difficult, and theoretical understanding relies on quantum mechanical calculations that must account for the behavior of electrons and nuclei under conditions far from everyday experience. The metallic transition happens gradually rather than at a sharp boundary, the conductivity increasing progressively as more electrons delocalize and join the conducting electron sea. The transformation occurring across a pressure range spanning perhaps a factor of 2 in pressure, from around 1 megabar to 2 megabars, depending on temperature and the exact path through pressure-temperature space. The metallic hydrogen layer that you are now entering extends from the metallization depth downward through thousands of kilometers towards Saturn's core region. This layer, containing most of Saturn's total mass and occupying most of its interior volume, the metallic phase representing the dominant state of matter within the planet. The material behaves as a liquid despite its metallic properties, the high temperature maintaining enough thermal energy that the hydrogen atoms remain mobile and flow continuously rather than crystallizing into a solid lattice. The combination of metallic electrical properties and liquid mechanical properties creating a conducting fluid unlike anything encountered in everyday terrestrial experience. This conducting liquid generates Saturn's magnetic field through dynamo action, electric currents flowing through the moving conductor and creating magnetic field through the same electromagnetic principles that govern electromagnets and electric generators. Electrical conductivity rises dramatically as you descend through the transition zone into fully metallic hydrogen. The resistance to electric current dropping from high values characteristic of insulators down to low values comparable to liquid metals. The delocalized electrons able to move freely in response to electric fields and carry current efficiently through the material. The conductivity affects how heat transports through this layer. Electrons carrying thermal energy through their motion and contributing to thermal conduction, in addition to the heat transport by convection that continues operating throughout the metallic layer. The enhanced thermal conductivity in metallic hydrogen compared to molecular or atomic hydrogen influences the temperature gradient, heat flowing more easily through the metallic regions and potentially modifying the convective patterns that operate here. Density continues increasing with depth, reaching values around 1 gram per cubic centimeter in the upper metallic hydrogen layer and climbing toward higher densities deeper down. The material compressing toward the densities of light metals while remaining chemically hydrogen, the single proton and single electron per atom, creating far lower mass per particle than the heavier elements that comprise terrestrial metals. The low atomic mass combined with high density means that particle number density reaches extreme values. Individual hydrogen nuclei packed together with separations approaching the size of atoms at normal pressure. The compression squeezing matter into configurations that maximize density, while quantum mechanical principles prevent complete collapse. The magnetic field pervades the metallic hydrogen layer, field lines threading through the conducting fluid and exerting forces on the currents flowing within it. The interaction between magnetic field and fluid motion, creating the coupling that maintains the field structure. The field strength measures in the range of tens to hundreds of microtesla in the outer portions of the metallic layer, values comparable to Earth's surface magnetic field. Though the field structure differs from Earth's, with Saturn's magnetic field showing more symmetry and closer alignment between magnetic axis and rotation axis. The field originates from currents flowing in the deeper portions of the metallic hydrogen layer, where convection and rotation combine to stretch and twist field lines and generate new magnetic flux through dynamo processes. Convection operates throughout the metallic hydrogen layer, warm fluid rising from deep interior levels, while cooler fluid sinks back down. The circulation driven by the heat flowing outward from Saturn's hot core region toward the cooler upper layers. The convection cells extend across thousands of kilometers, their vertical extent comparable to the layer thickness. The rising and sinking motions organized by Saturn's rotation through Coriolis forces that deflect moving fluid and create patterns that align with the rotation axis. The rotation organizes the convection into columnar structures, vertical cylinders of rising or sinking fluid aligned parallel to the spin axis. This organization affecting how the dynamo operates and contributing to the symmetry of Saturn's magnetic field. Compared to more chaotic fields generated in planets where convection shows less rotational organization, temperature increases towards 20,000 degrees Celsius as you descend deeper into the metallic hydrogen ocean. The thermal energy now comparable to the ionization energies of many elements, though hydrogen, with its single electron, has long since entered the regime where that electron delocalizes through the metallization process, rather than through thermal ionization. The heat content per unit volume becomes substantial. The dense, hot fluid storing enormous amounts of thermal energy. The interior of Saturn containing enough heat to maintain its current temperature for billions of years, even without ongoing heat sources. Though the heat generation from gravitational contraction and possibly helium rain provides continuing energy input that maintains heat flow across such long timescales. Pressure climbs past 5 megabars, 5 million times Earth's atmospheric pressure. The weight of Saturn's outer layers, creating forces that compress the metallic hydrogen, to densities approaching 1.5 grams per cubic centimeter, denser than many terrestrial liquids, despite the low atomic mass of hydrogen. The material resists further compression through quantum mechanical effects, the Pauli exclusion principle preventing electrons from occupying identical quantum states and creating pressure that opposes gravitational compression. The balance between degeneracy pressure and gravitational force helping determine the relationship between pressure and density in the deep interior. The equation of state, the relationship describing how pressure, temperature, and density relate to each other, becomes complex at these extreme conditions, where quantum mechanics and thermal motion both contribute significantly to the material properties. The dynamo process that generates Saturn's magnetic field operates most effectively in the deeper portions of the metallic hydrogen layer, where conductivity reaches its highest values and where vigorous convection creates the fluid motions that stretch and amplify magnetic field lines. Convection in a rotating conducting fluid naturally generates magnetic field through the induction process, where moving conductor experiences electric fields that drive currents, which in turn create magnetic field that reinforces and organizes the flow pattern. The self-sustaining feedback between flow and field maintains Saturn's magnetic field against ohmic dissipation, the continual stirring of the conducting fluid adding energy to the field faster than resistance drains it away. The dynamo operating continuously across billions of years, with only slow changes in field strength and structure. Helium remains mixed with hydrogen throughout most of the metallic layer, though the proportion may vary with depth if helium precipitation occurs at certain pressure and temperature conditions within this region. Some models suggest helium becomes less soluble in metallic hydrogen than in molecular or atomic hydrogen. The different electronic structure of the metallic phase potentially affecting how helium atoms interact with the surrounding hydrogen. If phase separation occurs, helium-rich droplets would form and sink through the lighter hydrogen-rich fluid. The settling process, releasing energy and potentially creating composition gradients where helium concentration increases toward the base of the metallic hydrogen layer and decreases toward its top. The spacecraft descends through the metallic hydrogen ocean. Thousands of kilometers of this exotic material surrounding you in all directions. The environment, utterly unlike anything at Earth's surface, but governed by the same fundamental physics that applies everywhere in the universe. The metallic hydrogen layer represents the heart of Saturn's mass distribution, the region containing the bulk of the planet's material and hosting the dynamic processes that generate the magnetic field and transport heat from core to surface. Below lies the transition to the core region where heavier elements concentrate, where rock and ice compressed to extreme density may comprise a distinct central mass, or where the metallic hydrogen may simply grade continuously into hydrogen enriched with heavy elements without sharp boundary. The interior structure, still uncertain from the limited observational constraints available to planetary scientists. The journey continues deeper into pressures and temperatures that exceed the metallic hydrogen layer's upper regions by factors of several, carrying you toward the innermost zones where density and temperature reach their peak values, and where Saturn's formation history remains preserved in the composition and structure of its central regions. Your spacecraft travels through the deep metallic hydrogen layer, where pressure exceeds 10 million bars, and temperature climbs past 50,000 degrees Celsius. The environment representing conditions more extreme than those found anywhere else in the solar system, outside the Sun itself. The compressed hydrogen, bearing little resemblance to the gas familiar from terrestrial experience, despite being composed of the same simple atoms. The material around you flows in powerful convection currents, thermal energy from the core region driving circulation that carries heat outward toward the surface thousands of kilometers above. The flow organized into columnar structures aligned with Saturn's rotation axis and spanning vertical distances that dwarf Earth's entire diameter. Density reaches values approaching 2 grams per cubic centimeter in the deepest regions you are traversing. The metallic hydrogen compressed to densities exceeding many common rocks, while remaining fluid and mobile under the extreme temperatures that maintain thermal motion sufficient to prevent solidification. The metallic hydrogen ocean extends thousands of kilometers in depth, the layer thickness comparable to the distance from Earth's surface to its core. This vast ocean of conducting fluid, comprising more than 90% of Saturn's total mass and defining the planet's overall structure. The material possesses electrical conductivity comparable to liquid metals like mercury, electrons moving freely through the medium and carrying current in response to electric fields. The high conductivity creating strong coupling between the magnetic field and fluid motion that shapes both the field structure and the flow patterns. The conducting fluid participates in organized circulation, driven by heat from below and organized by rotation from Saturn's 10-hour spin period. The rapid rotation, creating strong Coriolis forces that deflect moving fluid and establish the columnar convection pattern that characterizes deep planetary interiors. Convection currents transport heat upward through the metallic hydrogen layer at rates sufficient to carry Saturn's total heat output from the core region to the surface, the fluid motion providing far more efficient heat transport than thermal conduction alone could achieve, despite the enhanced conductivity of the metallic state. Rising currents carry hot material from the bottom of the metallic hydrogen layer toward the top, where the material cools and becomes denser, the cooling causing the fluid to sink back down in descending currents that complete the circulation pattern. The convection operates on timescales of years to decades, fluid parcels taking human lifetime timescales to complete one circuit from bottom to top and back down again. The slow, steady circulation, maintaining heat flow that has continued since Saturn's formation 4.5 billion years ago. Temperature increases toward 100,000 degrees Celsius as you descend through the deepest regions of the metallic hydrogen ocean. The heat content per unit volume now comparable to stellar surface values, though the high density means that thermal energy per particle remains moderate compared to the kinetic energies in stars. The extreme temperature results from gravitational compression converting potential energy into heat, and from the heat flow originating in the core region below, the combined effects maintaining temperatures that would vaporize any ordinary material, but which the metallic hydrogen withstands through the quantum mechanical pressure that prevents complete collapse. The high temperature creates thermal pressure that opposes gravitational compression. The balance between thermal pressure, degeneracy pressure, and gravity determining the density profile through this layer. Pressure approaches 40 million bars as you near the bottom of the metallic hydrogen layer. The weight from all of Saturn above compressing this deep region to pressures that exceed Earth's central pressure by factors of several. The conditions representing the highest sustained pressures naturally occurring anywhere in the solar system, outside Jupiter's deeper interior and the Sun. The material at these pressures shows properties that laboratory experiments struggle to replicate. Diamond anvil cells and shockwave experiments reaching these pressures only briefly and in tiny volumes. The sustained conditions in Saturn's interior, requiring planetary masses to create and maintain. Theoretical understanding of hydrogen behavior under these conditions relies on quantum mechanical calculations that solve for electron and nuclear configurations under the relevant conditions. The computational results providing predictions for density, temperature, and other properties that cannot be measured directly. The magnetic field strength reaches higher values in the deep metallic hydrogen layer than at the surface. Field lines concentrated by the flow patterns and by the geometry of the dynamo region. The field measuring thousands of microtesla in certain regions where organized currents create local enhancement. The field structure shows the effects of the convection pattern, columnar flow, organizing the field into configurations that align with the rotation axis and create the observed dipole character of Saturn's external field. The field and flow couple strongly, magnetic forces affecting fluid motion, while fluid motion generates and maintains the field. The nonlinear interaction creating complex dynamics that vary slowly over timescales of decades to centuries as the convection pattern evolves. Rotation organizes the metallic hydrogen layer into zones of differential rotation at shallow depths, where magnetic coupling remains weak. But deeper into the conducting region, the magnetic field eventually becomes strong enough that field lines resist being stretched by differential motion. The magnetic tension forcing the fluid into corotation, where all material rotates at the same angular velocity, regardless of distance from the rotation axis. This transition from differential rotation to solid body rotation occurs somewhere in the metallic hydrogen layer, at depths where magnetic field becomes strong enough to overcome the forces driving differential motion, the exact depth depending on poorly constrained properties like electrical conductivity and convection vigor. Below the transition depth, the entire interior rotates as a unit. The rotation period of the deep interior defining Saturn's true rotation period that cannot be measured directly from cloud motions, since atmospheric winds create variable surface rotation rates. Helium concentration may vary with depth through the metallic hydrogen layer if phase separation occurs. Models suggesting helium could become immiscible in metallic hydrogen under certain pressure-temperature conditions found in Saturn's interior. If separation occurs, helium-rich regions would sink through the hydrogen-rich fluid due to helium's higher atomic mass. The separation process creating composition gradients, where helium concentration increases with depth through the metallic layer. The settling helium would eventually accumulate at the base of the metallic hydrogen layer, or become incorporated into the core region. The depletion of helium from the upper layers, consistent with observations showing Saturn's atmosphere, contains less helium than expected from solar composition. Though the exact mechanism and location of separation remain subjects of ongoing research, the spacecraft continues descending through the metallic hydrogen ocean, the environment around you consisting of fluid hydrogen, compressed and heated to conditions that transform it into a conducting liquid metal. The material simultaneously familiar as the most common element in the universe. and exotic through the extreme state imposed by planetary scale pressures and temperatures. The darkness remains complete, no light penetrating from above, and the thermal radiation at these temperatures falling in ultraviolet and soft X-ray wavelengths. Invisible to human eyes, though detectable by instruments, the spacecraft's sensors registering the electromagnetic radiation while also monitoring the intense heat that flows through this region. The convection currents create flows that buffet your vehicle, density and temperature variations in the passing fluid, creating forces that the navigation systems compensate for continuously, maintaining descent trajectory through the circulation patterns that would otherwise deflect your path. Velocity measurements show the metallic hydrogen rotating with Saturn's deep interior rotation period, the magnetic coupling having locked the fluid into corrotation, despite the differential rotation visible in the atmosphere thousands of kilometers above. The organized rotation rate of approximately 10 hours and 33 minutes defines how fast the deep interior spins. This value representing Saturn's true rotation period, determined from measurements of magnetic field variations detected by spacecraft passing through the magnetosphere. The entire metallic hydrogen ocean rotates at this rate, billions of tons of conducting fluid circling Saturn's axis. In organized motion, the rotation creating centrifugal effects that contribute to the planet's oblate shape, visible from outside. Your spacecraft descends through this rotating fluid, moving with the rotation rather than fighting against it. The reference frame, tied to the deep interior, rather than to the differentially rotating atmosphere far above. The sense of depth becomes profound as you consider the distance already traveled from the cloud tops where your descent began. The journey through molecular hydrogen atmosphere and then through the transition zone, now supplemented by thousands of kilometers of passage through metallic hydrogen ocean. Saturn's interior contains layer upon layer of material, organized by pressure and temperature, each layer possessing distinct physical properties determined by the conditions at that depth. The total structure representing the equilibrium configuration that gravity and pressure establish over billions of years. The metallic hydrogen layer represents the largest component of this structure, the dominant reservoir of mass, and the primary heat transport mechanism that carries thermal energy from the core to the surface, where it radiates into space. The temperature and pressure conditions you experience in this deep metallic hydrogen region match those predicted to exist in the interiors of many other planets, both within our solar system and in exoplanetary systems discovered around other stars. Jupiter contains an even more extensive metallic hydrogen layer, extending deeper and experiencing higher pressures due to that planet's greater mass, while Uranus and Neptune likely possess smaller metallic hydrogen regions, or perhaps none at all, depending on whether their internal pressures reach the metallization threshold. Among exoplanets, the hot Jupiters and other giant worlds probably contain metallic hydrogen layers, similar to Saturn's. The conditions arising naturally whenever hydrogen accumulates in sufficient quantity that self-gravity compresses the interior to millions of bars pressure. The fluid around you carries the entire history of Saturn, encoded in its motion patterns and composition gradients, the convection currents having circulated for billions of years, and slowly mixed material from different regions, while also maintaining the separation between metallic hydrogen and the molecular hydrogen above. The helium that may have separated from the hydrogen over time has been sinking through this layer for hundreds of millions of years, the slow rain of helium droplets continuing today just as it has throughout much of Saturn's history. Heat from the core has been flowing upward through this conducting ocean since the planet's formation, the temperature gradients and convection patterns adjusting gradually as the core slowly cools and as the planet's internal heat generation decreases over geological time. Your instruments detect trace amounts of heavier elements mixed with the metallic hydrogen, small concentrations of water, methane, ammonia, and rocky material that dissolved into or became suspended in the hydrogen during Saturn's formation, when all the planet's components mixed together. These heavier materials may have settled toward the core region over time, their higher density causing them to sink through the lighter hydrogen, but some fraction remains distributed through the metallic layer, where convection continues to transport it. The presence of these materials affects the properties of the metallic hydrogen slightly, changing its density and conductivity by small amounts, the variations contributing to the detailed structure of the magnetic field and convection pattern. The bottom of the metallic hydrogen layer approaches as pressure increases, beyond 40 million bars, and as density continues climbing toward values that suggest transition to a different compositional zone. Below lies the core region where heavier elements concentrate, where rock and ice compressed to exotic states may form a distinct boundary or may grade continuously into the metallic hydrogen without sharp transition. Your descent carries you toward that boundary, the final stage of the journey into Saturn, approaching as you leave the metallic hydrogen ocean and enter the innermost region where the planet's formation began and where the heaviest materials have accumulated over billions of years. The spacecraft adjusts its trajectory in preparation for entering the core transition zone, the navigation systems calculating the path that will carry you through whatever structure exists at Saturn's center. The metallic hydrogen around you continues its slow circulation. Unconcerned with your passage through it, the convection currents and magnetic fields and rotation patterns continuing as they have for eons and will for eons more. You prepare for the final descent, the ultimate depth, the journey to Saturn's heart, where conditions reach their most extreme values and where the last mysteries of the planet's interior await. You descend below the metallic hydrogen ocean into regions where models predict heavier elements begin to dominate over pure hydrogen, the transition zone between the metallic hydrogen layer and whatever core structure exists at Saturn's center, representing one of the least understood regions of the planet's interior. The pressure here exceeds 45 million bars, the weight of all of Saturn above, compressing this region to values that dwarf the pressures found anywhere else in the solar system, except at the very centers of Jupiter and the Sun. The extreme conditions forcing matter into configurations that laboratory experiments cannot replicate, and that theoretical models struggle to predict with confidence. Temperature climbs above 100,000 degrees Celsius. Heat flowing upward from the core region and generated locally by the compression of material to ever higher densities as your descent continues deeper. The composition of the material around you shifts from pure metallic hydrogen to a mixture that includes increasing amounts of water, methane, ammonia, and rocky compounds. These heavier substances having settled towards Saturn's center over billions of years due to their greater mass compared to hydrogen and helium. The water at these pressures and temperatures bears no resemblance to liquid water or ice as known from Earth. The molecules dissociated by the heat and compressed into configurations where oxygen atoms form structures, while hydrogen ions move separately through the material. Methane similarly breaks down into carbon and hydrogen, the carbon potentially forming diamonds or other high-pressure carbon phases, while hydrogen dissolves into the surrounding fluid or recombines into different compounds. Ammonia decomposes into nitrogen and hydrogen under these conditions, the nitrogen potentially forming exotic compounds with other elements present in this layer, or existing as separate nitrogen-rich phases. Rocky material, silicates, and iron compounds that condensed from the solar nebula during Saturn's formation compresses into high-pressure crystal structures different from the minerals familiar at Earth's surface, the atoms packed more closely and arranged in geometries that minimize volume under the extreme compression. The mixture of all these materials creates a heterogeneous environment where composition varies with depth and possibly with location, convection and settling having organized the materials according to density, while mixing prevents complete separation. The concept of distinct layers becomes less clear at these depths. The transition from metallic hydrogen to core material, possibly occurring gradually over thousands of kilometers rather than at a sharp boundary. Models suggest heavier elements may be dissolved in metallic hydrogen at the top of the core region, the concentration increasing smoothly with depth as more heavy material accumulates. The mixture eventually becoming dominated by rock and ice compounds rather than hydrogen. Alternative models propose a more distinct boundary where metallic hydrogen ends abruptly and core material begins, the two regions separated by a transition zone only hundreds of kilometers thick, where properties change rapidly with depth. Your instruments measure density approaching 3 grams per cubic centimeter, the value exceeding typical rock densities, despite the high temperatures that would normally cause thermal expansion. The extreme pressure overcomes thermal effects, compressing the material to densities determined primarily by how closely atoms can pack under the applied force. The temperature contributing through thermal pressure that opposes compression but unable to overcome the gravitational weight of the planet above. Electrical conductivity remains high in this region. The mix of metallic hydrogen, ionized water, and other conducting phases maintaining pathways for electric current that keep this layer involved in the magnetic field generation, despite the changing composition. Heat flow through this region continues upward from the core below. Convection in the core transition zone, carrying thermal energy toward the metallic hydrogen layer above where the heat joins the upward flow that eventually reaches Saturn's surface. The convection in this mixed composition layer operates differently than in the pure metallic hydrogen ocean. The presence of multiple components with different properties creating more complex flow patterns. Heavier materials tend to settle downward, while lighter components rise. The composition-driven convection combining with temperature-driven convection to create circulation patterns that vary with both depth and composition. Temperature measurements show values approaching 150,000 degrees Celsius in the deepest regions you traverse. The heat, originating from multiple sources, including the slow cooling of primordial heat trapped during Saturn's formation, and the release of gravitational energy as heavier materials continue settling toward the center. Radioactive decay of elements like uranium, thorium, and potassium in the rocky component contributes additional heat, though the amounts remain small compared to the primordial heat and gravitational energy. The combination of heat sources maintains temperatures that keep the core region fluid and mobile, despite the extreme pressures that would favor solid phases at lower temperatures. The spacecraft encounters increasing resistance as density continues rising. The viscosity of the material through which you travel increasing as composition shifts toward heavier elements and as pressure compresses the fluid to values where flow becomes more difficult. Navigation systems work continuously to maintain descent trajectory, compensating for the varying properties of the medium and for the convection currents that create regions of upward and downward flow. The darkness around you remains absolute. Thermal radiation at these temperatures falling at wavelengths your instruments detect, but no visible light penetrating this deep into Saturn's interior from any external source. Pressure approaches 50 million bars as you continue deeper, the conditions now exceeding pressures found anywhere in Earth's interior and matching those predicted for the deep interiors of ice giant planets like Uranus and Neptune. The material responds to these pressures by adopting exotic structures, water forming superionic ice phases where oxygen atoms arrange in crystal lattice, while hydrogen ions flow freely through the structure like electrons in a metal. The material simultaneously solid and liquid, with different components showing different behaviors. This superionic water can conduct electricity through the mobile hydrogen ions, the conductivity contributing to the overall electrical properties of the core transition zone. Rocky material at these pressures adopts structures different from surface minerals, silicon and oxygen, and metal atoms packing into configurations that minimize volume while maintaining electrical neutrality. Some models suggest these high-pressure silicates might decompose into separate oxide phases, magnesium oxide and silicon dioxide, separating into distinct layers, according to density, though the mixing from convection could prevent complete separation. Iron, if present in sufficient quantities, might separate from silicates and sink toward the very center, creating an iron-rich innermost core, similar to Earth's core, though at much higher temperatures and in a fully liquid state. The sense of approaching Saturn's center becomes palpable as depth increases and as the character of the material around you shifts from the relatively simple metallic hydrogen ocean to this complex mixture of multiple phases and compositions. You travel through the region where Saturn's formation began, where the original core of rock and ice accreted from the solar nebula before the massive hydrogen and helium envelope was captured through gravitational attraction. The heavy elements around you represent some of the first solid material that condensed from the cloud of gas and dust surrounding the young sun 4.5 billion years ago, these atoms having been locked in Saturn's interior ever since. The rocky and icy materials you pass through came from the outer solar system region, where Saturn formed, the zone beyond the ice line, where water and other volatiles could condense into solid form. The rock originated from silicate dust and larger solid particles that survived from the solar nebula's collapse, while the ice formed when water vapor and other gases froze onto grained surfaces and condensed into larger bodies. These materials accumulated through collisions and gravitational attraction, building first into small planetesimals and eventually into a core massive enough to gravitationally capture hydrogen and helium gas from the surrounding nebula. the captured gas forming the thick envelope through which you descended to reach this deep region. Your position now lies thousands of kilometers below Saturn's visible cloud tops, the journey having carried you through the molecular hydrogen atmosphere, through the transition to metallic hydrogen, through the deep metallic hydrogen ocean, and now into the core transition zone, where composition complexity peaks. Above you stretch all the layers you traversed, each zone characterized by distinct physical and chemical properties, determined by the local pressure, temperature, and composition. The entire structure held together by Saturn's gravity and organized by billions of years of evolution and differentiation. The material properties around you represent extremes of pressure and temperature that transform familiar substances into exotic states unknown in everyday experience. Water becoming superionic ice, rock adopting high-pressure crystal structures, methane decomposing into diamond and hydrogen. All these materials mixed together and stirred by slow convection that has operated throughout Saturn's history. The conditions test the limits of our understanding of matter. The behavior of materials under such extremes requiring quantum mechanical calculations and uncertain extrapolations from laboratory data gathered at lower pressures. The predictions carrying significant uncertainties that observations of Saturn from outside cannot easily resolve. The spacecraft continues descending through the core transition zone, the final kilometers of your journey approaching as you aim for Saturn's central region, where the ultimate depth awaits. The core's true nature remains uncertain, whether a distinct boundary separates it from the transition zone, whether a solid inner core exists at the very center, whether composition varies smoothly or in discrete layers. All these questions lacking definitive answers due to the difficulty of measuring properties so deep inside the planet. Your descent will carry you to the very center, to the point around which all of Saturn's mass distributes itself, to the heart of the giant planet. The environment grows denser still as you approach the core boundary, pressure climbing towards 60 million bars, temperature exceeding 150,000 degrees, density reaching values between 3 and 4 grams per cubic centimeter, depending on the exact composition of the material at this depth. The conditions represent the most extreme naturally occurring environment in the Saturn system, exceeded elsewhere in the solar system only by the interiors of Jupiter and the Sun. The compressed and heated material existing in states that bridge the gap between ordinary matter and the exotic conditions found in stellar cores. You cross into what models identify as Saturn's core region, the innermost zone where heavier elements dominate, completely over hydrogen and helium, where rock and ice compressed to exotic densities comprise most of the material, where the conditions reach their maximum extremes of pressure and temperature for any location in the planet's interior. The transition feels gradual rather than sudden, density increasing smoothly from the mixed composition of the transition zone to the heavy element-dominated core, the boundary representing a change in which component dominates, rather than a sharp interface between different materials. Pressure here exceeds 55 million bars and continues rising as you descend toward the center. The weight of all of Saturn compressing this innermost region to values that approach 60 million bars at the very heart. Temperature measurements show values near 160,000 degrees Celsius. The heat maintained by the slow cooling of primordial thermal energy and by the ongoing gravitational energy release, as heavier materials continue settling toward the center, and as the entire planet slowly contracts under its own weight. The extreme temperature keeps the core material fluid, despite pressures that would favor solid phases at lower temperatures. The thermal motion of atoms remaining vigorous enough to prevent the material from freezing into a solid state. Some models suggest a small solid inner core might exist at the very center where pressure finally overcomes thermal effects. Though the evidence remains inconclusive, and the solid region, if present, would represent only a small fraction of the total core mass. The composition around you consists primarily of rock and ice, compressed to high-pressure phases. The rock component including silicates, where silicon and oxygen combine with magnesium, iron, and other metals, along with possible metallic iron, if differentiation has separated it from the silicate phases. The ice component includes water in superionic or other high-pressure forms, along with compressed methane-derived carbon that may exist as diamond or other carbon phases, and ammonia-derived compounds containing nitrogen. The proportions of rock to ice remain uncertain, estimates ranging from roughly equal amounts to rock-dominated compositions, depending on which models of Saturn's formation and evolution prove correct. Superionic ice pervades much of the core region, water existing in a state where oxygen atoms form a regular crystal lattice, while hydrogen ions move freely through the structure, like a fluid. The oxygen lattice providing mechanical strength, while the mobile hydrogen ions carry electric current. This phase of water forms only under the specific combinations of pressure and temperature found in planetary interiors, the conditions requiring both sufficient compression to organize the oxygen atoms and sufficient temperature to mobilize the hydrogen ions. The superionic ice contributes to the core's electrical conductivity. The moving hydrogen ions carrying current that couples to Saturn's magnetic field and potentially generates magnetic field components through dynamo action in the core region itself. Rocky material at these pressures adopts post-perovskite structures and other high-pressure crystal forms, where atoms pack more closely than in familiar surface minerals. The silicon-oxygen bonds compressed and modified by the extreme conditions. Some theoretical work suggests silicates might break down into separate oxide phases. At the highest pressures, magnesium oxide separating from silicon dioxide, each phase adopting its own high-pressure crystal structure. If iron is present in significant quantities, as metallic iron rather than incorporated in silicates, it might sink to the very center and form an iron-rich innermost region, though whether sufficient iron exists and whether differentiation proceeded far enough to separate it remain open questions. The density around you measures between 3 and 5 grams per cubic centimeter, depending on exact composition and depth, the value exceeding the density of typical rocks at Earth's surface, despite the high temperature that would normally cause expansion. The compression overcomes all thermal effects, packing atoms to separations determined by the balance between gravitational pressure and the quantum mechanical forces that prevent electrons from occupying the same states. The material resists further compression through degeneracy pressure, where quantum effects begin contributing significantly to the total pressure. Though Saturn's core does not reach the extreme compression found in white dwarf stars, where degeneracy pressure dominates completely, heat flows outward from the core, through both convection and thermal conduction. The high temperatures creating temperature gradients that drive heat flux toward the overlying layers. Convection in the core operates where temperature gradients exceed the adiabatic gradient. Fluid regions becoming unstable and overturning to transport heat more efficiently than conduction alone could achieve. The convection pattern depends on the core's composition and structure, uniform composition creating different flow patterns than stratified layers where composition varies with depth and potentially suppresses convection in some regions, while enhancing it in others. Your spacecraft descends through the core region, the environment around you consisting of compressed rock and ice, heated to temperatures that would vaporize them at normal pressures. The material held in fluid form by the extreme compression that keeps even these high temperatures insufficient to overcome the pressure-induced density. The darkness remains absolute, no light from any external source reaching this depth. The thermal radiation at core temperatures falling at X-ray and extreme ultraviolet wavelengths that your instruments detect but that provide no illumination in any familiar sense. The spacecraft's sensors monitor temperature, pressure, density, and composition. The measurements providing data about this inaccessible region that cannot be studied through any means other than theoretical models and inference from external observations. Electrical currents flow through the conducting core material. The combination of superionic ice, possibly liquid metals, and other conducting phases, allowing electric current to circulate in response to the magnetic field and to motions of the conducting fluid. These currents contribute to magnetic field generation through dynamo processes, though the main dynamo region likely resides in the metallic hydrogen layer, above where larger volume and more vigorous convection create stronger field-generating effects. The core's contribution to the total magnetic field remains uncertain, some models suggesting it plays a significant role, while others consider it secondary to the metallic hydrogen dynamo. The gravitational acceleration you experience begins decreasing as you descend deeper into the core, the effect arising because the mass above you, the material at larger radii, pulls outward and partially cancels the inward pull from mass below. Near the center, gravitational acceleration approaches zero as the mass distributes nearly equally in all directions around you. The net gravitational force vanishing at the exact mathematical center, even though the gravitational potential reaches its minimum there. This decreasing gravity affects the pressure gradient, pressure increasing more slowly with depth near the center than in the outer regions where gravity remains strong. The core material around you contains the original seeds from which Saturn grew, the rock and ice that accreted in the outer solar system during the first few million years after the sun's formation. These atoms came from the material ejected by previous generations of stars, the heavy elements forged in stellar fusion and supernova nucleosynthesis during the billions of years before our solar system formed. The oxygen in the water ice, the silicon in the rock, the carbon in the methane, the iron in the metal. All these atoms were created inside stars and released when those stars died, the material mixing with hydrogen and helium from the Big Bang, and collecting into the cloud that eventually formed the sun and planets. This core material accumulated first, growing through collisions between smaller bodies until a core of perhaps 10 or 15 Earth masses had formed. At that point, the core's gravity became strong enough to attract and hold onto hydrogen and helium gas from the surrounding solar nebula, the gas accretion proceeding rapidly once it began and adding the vast hydrogen-helium envelope through which you descended. The core itself likely grew somewhat during gas accretion as additional rock and ice mixed with the infalling gas. Some models suggesting the core might have partially dissolved into the overlying metallic hydrogen over Saturn's history, redistributing some core material upward while a dense central concentration remained. The time depth at this location spans Saturn's entire history, the core material having existed in compressed, heated form for 4.5 billion years, since the planet's formation completed. The atoms around you have remained locked at Saturn's center through all of Earth's history, through the formation of the Moon, through the development of life on Earth, through the evolution of complex organisms, and eventually, humans, through all of recorded history and all of human existence. These atoms have been here in this extreme environment, slowly cooling and slowly evolving as Saturn ages. The timescales involved dwarf human experience, billions of years of patient existence in conditions of crushing pressure and extreme heat. Your instruments detect the composition signatures of the core material. Spectroscopic analysis of the thermal radiation, providing information about which elements and compounds are present, even though direct sampling remains impossible. The measurements confirm the presence of oxygen, silicon, carbon, nitrogen, and metals in abundances consistent with the rock and ice composition expected from Saturn's formation in the outer solar system. Hydrogen remains present even at these depths, mixed with the heavier materials and contributing to the overall composition despite the core region being dominated by heavy elements. The structure of the core, whether it contains distinct layers of different composition or whether it remains relatively uniform, affects how heat flows out and how the material convects. Layered structures, where dense iron-rich material underlies lighter silicate-rich material, which underlies ice-rich material, could suppress convection at the layer boundaries, the density steps resisting vertical motion and creating stable stratification. Uniform composition allows more vigorous convection throughout the core volume, heat transport becoming more efficient, and temperature gradients becoming less steep. The different scenarios producing different thermal evolution and different current states that observations from outside Saturn cannot easily distinguish. The spacecraft continues its descent towards Saturn's geometric center, the final kilometers of the journey remaining as you approach the mathematical point that defines the very heart of the planet. The core material around you extends in all directions. The environment isotropic at these depths, where no preferred direction exists except the faint remaining gravitational gradient pointing toward the center. You approach the ultimate destination, the end point of this journey from the outer rings, through the atmosphere and interior, to the deepest possible depth, the very center of Saturn, where your exploration will conclude. You reach the innermost region of Saturn's core, where the distance to the geometric center measures only a few hundred kilometers. The conditions here, representing the most extreme environment naturally occurring anywhere in the Saturn system. Pressure peaks near 60 million bars, the maximum value reached anywhere in the planet's interior. The weight of all of Saturn's mass bearing down on this central region and compressing the material to densities approaching 5 grams per cubic centimeter. Temperature reaches approximately 160,000 degrees Celsius. The thermal energy maintained by the slow release of primordial heat and by gravitational energy as the planet continues its gradual contraction. The extreme temperature keeping the material fluid and mobile despite the crushing pressure that surrounds you. The composition at this depth consists of the densest materials that settled to Saturn's center during the planet's formation and evolution. Rock and possibly metallic iron comprising much of the mass, with compressed ice phases mixed throughout. The silicon and oxygen that form the silicate rock component exist in high-pressure crystal structures where atoms pack as closely as quantum mechanics permits. The electron shells, compressed and deformed by the extreme pressure. Iron, if present in metallic form, would concentrate at the very center where its high density allows it to sink below the lighter silicates, creating an iron-rich core within the core. Though whether Saturn contains sufficient iron and whether separation proceeded this far remain uncertain. Water, in superionic ice form, fills spaces between rock grains or forms separate regions, the oxygen lattice providing structure while hydrogen ions flow through freely. Carbon from decomposed methane may exist as diamond crystals formed under the extreme pressure, the carbon atoms locked in the strong covalent bonds characteristic of diamond structure. Tiny crystals or larger formations embedded in the surrounding rock and ice matrix. Nitrogen from ammonia breakdown exists in various compounds. The nitrogen chemistry at these conditions remaining poorly understood but potentially forming unusual phases that incorporate nitrogen into structures with other elements. The material around you has existed in this extreme state for 4.5 billion years, compressed and heated since Saturn's formation, completed during the solar system's earliest epochs. The atoms here came from the pre-solar nebula, material contributed by dying stars during the millions or billions of years before our solar system formed. Heavy elements forged through nuclear fusion in stellar cores and through supernova nucleosynthesis when massive stars exploded. These particular atoms participated in stellar nucleosynthesis, were ejected into space, drifted through the interstellar medium, eventually entered the molecular cloud that collapsed to form our solar system, condensed into solid particles in the outer solar nebula, accreted into larger bodies, and finally collected into Saturn's core, where they have remained ever since. The gravitational acceleration at this depth drops to nearly zero. The mass of Saturn, distributed almost equally in all directions around you, creates gravitational forces that cancel each other almost completely. At the exact mathematical center, gravitational acceleration becomes exactly zero, all of Saturn's mass pulling outward with perfect symmetry. The net force vanishing even though you remain deep in Saturn's gravitational potential well. This peculiarity of being at the center means that pressure here results not from local gravitational force, which vanishes, but from the pressure transmitted from surrounding regions where gravity remains strong and compresses material inward. You observe the environment around you, the compressed rock and ice, glowing with thermal radiation at extreme ultraviolet and soft X-ray wavelengths, the material hot enough that thermal velocities of atoms reach high energies. The core material flows slowly in convection patterns, if composition permits. Heat from the very center rising toward the overlying transition zone, where it joins the upward heat flow that continues through the metallic hydrogen layer. and eventually reaches Saturn's surface, thousands of kilometers above. The convection velocities remain modest, perhaps millimeters per second, the slow circulation transporting heat outward, while the high viscosity of the compressed material resists rapid flow. The magnetic field lines thread through this central region, field generated in the metallic hydrogen layer above, penetrating through the core and creating complex patterns where the field interacts with any electric currents flowing in the conducting core material. The field strength varies with position, some regions experiencing stronger fields than others, depending on the convection pattern in the metallic hydrogen and on any field generation occurring within the core itself. The field connects this deep interior to Saturn's external magnetosphere. The field lines providing the link between the planetary dynamo and the magnetic structure that extends into space and interacts with the solar wind. Your position at Saturn's center places you at the reference point from which the entire planet's structure radiates outward, the core region extending several thousand kilometers around you. Then the core transition zone, where heavy elements mix with metallic hydrogen. Then the deep metallic hydrogen ocean spanning tens of thousands of kilometers. Then the molecular hydrogen envelope. Then the atmosphere with its visible clouds and weather systems. And finally, the rings spreading in the equatorial plane far above. All of this structure exists in equilibrium under Saturn's gravity, each layer occupying the radial range where pressure and temperature create conditions appropriate for that composition and phase. The journey from the outer ring system to this central point has traversed the full range of Saturn's structure, passing through each distinct region and experiencing the gradual changes in composition, pressure, temperature, and physical state that characterize the planet's interior. You traveled through the tenuous outer rings, where particles spread across enormous volumes, through the main rings, where ice chunks orbit in flat sheets, into the upper atmosphere, where hydrogen and helium remain in familiar gaseous form, down through the molecular atmosphere, where clouds form and storms develop, through the transition to metallic hydrogen, where pressure transforms the material into a conducting fluid, through the deep metallic hydrogen ocean, where convection and magnetic fields organize the interior, through the core transition zone, where heavy elements begin dominating, and finally to this core region where rock and ice compressed to extreme densities form Saturn's heart. Each layer revealed different physical processes and different states of matter, the diversity arising from the range of conditions that exist at different depths in a massive planet. The rings showed gravitational dynamics and orbital mechanics. The atmosphere displayed fluid dynamics and cloud physics. The molecular hydrogen layer demonstrated pressure-induced chemistry and phase transitions. The metallic hydrogen ocean exhibited exotic material properties and magnetic field generation. The core region showed extreme states of familiar substances transformed by pressure and temperature beyond everyday experience. The journey provided a tour through physics and chemistry, operating under conditions spanning from near vacuum in the outer rings to tens of millions of bars pressure at the center. Saturn itself represents one example of the giant planets common in our solar system and found around other stars throughout the galaxy. Worlds where hydrogen and helium dominate the composition, but where heavier elements also play important roles in the interior structure and evolution. Jupiter resembles Saturn in structure, but grows more massive and compresses its interior to even higher pressures, while Uranus and Neptune contain less hydrogen and helium relative to heavier elements, and may lack the extensive metallic hydrogen layers found in Saturn and Jupiter. Among exoplanets, giant worlds orbiting other stars likely show similar interior structures with metallic hydrogen layers and compact cores, the basic architecture arising naturally when planets accumulate massive hydrogen-helium envelopes. The time you spend at Saturn's center allows contemplation of the planet's long history and slow future evolution. Saturn formed 4.5 billion years ago, when the solar system was young, its core accreting first from solid materials in the outer solar nebula, then capturing its massive hydrogen-helium envelope when the core grew large enough to gravitationally attract gas. The planet heated during formation through gravitational energy release, then slowly cooled over billions of years, radiating away the primordial heat while contracting slightly and releasing additional gravitational energy. This slow cooling continues today, Saturn radiating more energy than it receives from the Sun. The excess coming from the ongoing contraction and possibly from helium separation, releasing gravitational potential energy. Billions of years into the future, Saturn will continue cooling and contracting, the interior temperatures gradually decreasing as heat radiates away into space. The planet will slowly shrink, its radius decreasing by small amounts as internal pressure drops slightly. With cooling, the contraction continuing until the planet reaches a cold equilibrium state, billions of years from now. The rings may be long gone by then, the particles either fallen into the planet or disrupted and scattered. The magnificent ring system, possibly a temporary feature visible only during a fraction of Saturn's total lifetime. The moons will continue orbiting, their orbits slowly evolving through tidal interactions and orbital resonances, the satellite system changing gradually over geological timescales. The core material around you will remain at Saturn's center through all this future evolution. The rock and ice that collected here during formation, staying compressed and buried beneath thousands of kilometers of hydrogen, regardless of how the planet's outer layers evolve. The atoms here may remain locked in place for tens of billions of years, persisting until the Sun eventually expands into a red giant and disrupts the solar system's architecture. Even then, possibly surviving in some remnant configuration. The timescales dwarf not just human history, but the entire future of life on Earth. The longevity of planets exceeding the longevity of the biosphere by comfortable margins. Your spacecraft has reached its ultimate destination, the journey from the outer rings to the very center complete, every layer traversed and every region observed during the continuous descent. The purpose was to experience Saturn from outside to inside, to understand through observation and measurement what exists at each depth, to follow the gradual progression from the familiar conditions of space and rings, through increasingly exotic environments, to the extreme states found at the core. The journey revealed Saturn not as a simple gas ball, but as a complex structured world with distinct regions characterized by different physics and different chemistry. The interior organization arising from the fundamental physics of matter under pressure. The view from here, if one could see through the surrounding material, would show Saturn's layers spreading outward in all directions, each spherical shell containing its characteristic composition and properties. The entire structure held together by gravity and maintained by the balance between pressure and gravitational force. The metallic hydrogen ocean above circulates slowly in organized convection. The molecular hydrogen envelope rotates with variable speeds at different latitudes. The atmosphere displays its banded structure, and storm systems, the rings spread in their elegant flat sheets, and space extends beyond, containing the moons and magnetosphere and solar wind. All of this complexity exists because hydrogen and helium and heavier elements, governed by gravity and quantum mechanics and thermodynamics, organize themselves into the equilibrium structure called Saturn. The time has come to conclude this journey. Having reached the point where no further descent remains possible, the geometric center approached as closely as the concept permits. You have traveled from the space outside Saturn through every layer of the planet to its heart, observing the structure that exists and understanding through the journey how giant planets organize their interiors. Saturn continues its ancient orbit around the Sun, its structure stable and enduring, its interior layers flowing and convecting, and slowly evolving over timescales that dwarf human experience. The journey completes here, at the center, at the point around which everything else rotates, at the heart of this magnificent world that has been home to this exploration through its full depth.